For more than a century, the name Megalodon has functioned as a symbolic ceiling. It represents the upper boundary of predatory scale ever accepted by mainstream paleontology. A shark exceeding 15 meters in length, possessing a bite force measured not merely in tons but in geological consequence, became the benchmark against which all hypothetical marine giants were dismissed. Anything larger was relegated to folklore, misinterpretation, or exaggeration, and yet the oceans have never operated according to human benchmarks. Beneath the assumptions embedded in fossil catalogs and comparative anatomy lies a structural bias. The ocean does not preserve its largest secrets well. The bigger the organism, the rarer the circumstances under which it fossilizes. Pressure collapses soft tissues, scavengers erase connective structures, and tectonic recycling consumes entire seabeds. What survives is fragmentary, ambiguous, and often misclassified. This bias grows exponentially with size. The prevailing narrative holds that ecological limits prevent marine predators from exceeding the dimensions of Ototus Megalodon. Energy availability, oxygen diffusion, structural support, all cited as constraints. These arguments assume a static ocean, uniform through time, governed by modern parameters. However, Earth's oceans have not been static. Temperature gradients, salinity layers, oxygenation depth, and primary productivity have fluctuated dramatically across geological epochs. At several points in Earth's history, the sea was not merely warmer, but denser, richer, and layered in ways no longer present. During certain intervals of the late Paleogene and early Neogene, the ocean functioned as a vertically stratified energy reservoir. Surface productivity was extreme, but more importantly, mid-water zones accumulated slow-moving biomass in unprecedented volumes. Vast belts of nekton drifted along thermal boundaries, neither surface-dwelling nor abyssal. This created ecological corridors, measured not in kilometers, but in thousands of kilometers. Continuous feeding grounds that favored size over speed. In such an environment, the selective advantage shifts. Gigantism ceases to be a liability. Efficiency replaces agility. Momentum replaces maneuverability. The ocean itself becomes structural support and, scattered across museum drawers and mislabeled collections, are remains that do not comfortably belong to any known taxon. Vertebral centra too wide relative to height. Dentition fragments that suggest crushing forces inconsistent with shark cartilage dynamics. Calcified elements exhibiting growth banding patterns. Incompatible with known elasmobranch life histories. For decades, these anomalies were explained away as deformation, pathology, or composite assemblages. Re-examination using modern imaging techniques tells a different story. Computed tomography reveals internal lattice structures indicating load-bearing adaptations beyond what cartilage alone can provide. Isotopic analysis suggests an organism operating at depths where pressure would cripple most large predators. Trace element ratios imply a metabolism neither fully ectothermic nor endothermic, but something intermediate, slow, persistent, and resilient. Growth rates inferred from banding patterns suggest lifespans measured not in decades, but in centuries. Size estimates derived from these fragments exceed established records not marginally, but categorically. Reconstructions remain controversial, but even conservative models indicate a body length surpassing Megalodon by several meters, with mass increasing non-linearly. The relationship between length and volume ensures that a modest increase in size results in a disproportionate increase in mass. What emerges is not merely a larger shark-like creature, but an organism occupying a different functional class entirely. Its body plan appears optimized for glide rather than pursuit. The axial skeleton suggests reduced lateral flexion, favoring long, energy-efficient cruising. Musculature attachment sites indicate slow contraction cycles, trading explosive speed for sustained force. Feeding mechanics reconstructed from jaw fragments imply a methodical engulfing strategy rather than rapid biting. This was not a hunter in the conventional sense. It was a moving geological event, and the question arises, how could such a creature remain undocumented? The answer lies not in its rarity, but in its invisibility. Large does not mean conspicuous. In fact, extreme size often correlates with behavioral withdrawal from surface interaction. Deep, slow-moving organisms intersect with human observation only by accident. Even modern oceans host animals whose full dimensions were underestimated for centuries, despite regular encounters. Moreover, this organism appears to have occupied a vertical niche, rarely sampled by both fossilization and observation, the mesopelagic-bathypelagic interface. Too deep for sunlight, too shallow for abyssal stability. A zone of perpetual twilight, characterized by migratory biomass and low disturbance. A place where size can hide in plain absence. Acoustic modeling based on inferred body mass suggests that such an organism would generate low-frequency pressure waves rather than sharp sounds. Its movement would not alert prey in the conventional sense, but subtly alter the water column ahead of it. Smaller organisms would drift into its path without perceiving a threat. Feeding would be continuous, passive, and devastatingly effective. Extinction, when it came, would not have been sudden. Gigantic specialists do not vanish quickly. Instead, their decline mirrors the slow unraveling of the systems that sustain them. Cooling oceans reduced stratification, nutrient flows shifted, migratory corridors fragmented. What once supported a singular, colossal presence became insufficient. Reproduction rates could not compensate. Juvenile survival collapsed. The ocean shrank, ecologically speaking, and by the time the last individuals disappeared, their absence would have gone unnoticed. No shoreline carcasses, no sudden ecological shock visible at human scale. Only a gradual reorganization of midwater food webs, interpreted millions of years later as background noise in the fossil record. What remains are gaps, discontinuities, measurements that refuse to align. And the persistent discomfort of scale, the sense that the largest predator we acknowledge may not, in fact, have been the largest to ever exist. Part I establishes a premise rather than a conclusion. The ocean has always been capable of more than it reveals. Size is not an anomaly in deep time. It is a recurring solution. The assumption that Megalodon represents an upper limit says more about human imagination than about marine evolution. And somewhere in the stratigraphic silence, the outline of something larger continues to emerge slowly, incompletely, and inevitably. To understand an organism that exceeds the scale of Megalodon, it is not sufficient to enlarge an existing model. Size alone does not produce viability. Beyond a certain threshold, anatomy must transform fundamentally. What emerges from the available evidence is not a magnified shark, but a structure adapted to laws that govern mass rather than speed, and the axial framework inferred from fragmentary remains suggests a departure from the flexible, whip-like spines characteristic of large pelagic predators. Instead, vertebral proportions indicate compression resistance as a priority. The centra are broad, flattened, and internally reinforced by trabecular networks arranged in radial geometries. These internal lattices distribute load across the entire body length, allowing the organism to maintain integrity under immense pressure without requiring constant muscular stabilization. Such a spine does not favor rapid turns. It favors stability. The implication is profound. This creature did not chase. It intercepted. Hydrodynamic modeling based on reconstructed cross-sections reveals a body profile optimized for laminar flow at low to moderate velocities. The anterior region tapers gradually, minimizing turbulence, while the midsection expands into a volumetric core capable of housing massive organ systems. Posterior narrowing is subtle rather than abrupt, indicating propulsion derived from long, slow oscillations rather than tail-driven bursts. The fin structures, where preserved impressions exist, suggest reduced surface area relative to total mass. This would be catastrophic for a fast-moving predator, but ideal for an organism that relies on inertia. Once in motion, stopping would be inefficient, but stopping was unnecessary. The ocean itself became a conveyor. Musculature attachment scars imply fibers arranged in thick, layered sheets rather than discrete bundles. Contraction cycles reconstructed from these patterns point to movements measured in seconds rather than fractions thereof. Each motion would displace enormous volumes of water, creating pressure gradients extending hundreds of meters outward. Prey need not be pursued. It would be drawn inward by hydrodynamic consequence. And the cranial remains, though incomplete, are among the most controversial. Jaw articulation surfaces indicate a gape exceeding that of Megalodon by a significant margin, but the dentition tells a different story. Teeth, where found, are not optimized for slicing. They are thick, blunt-edged, and deeply rooted. Some exhibit wear patterns consistent with repetitive compressive stress rather than cutting action. This suggests a feeding strategy centered on engulfment and crushing rather than predation via laceration. The jaws would open slowly, creating a pressure differential that pulled organisms inward. Closure would be gradual but unstoppable, compressing prey en masse. Bones fractured not by impact, but by sustained force. The mouth functioned less like a trap and more like a closing geological fault. Within the oral cavity, inferred soft tissue structures indicate filtration ridges, not unlike those found in some modern megafauna, but reinforced to withstand higher stress. This raises the possibility that feeding was opportunistic rather than selective. Schools, swarms, migratory columns all could be consumed without differentiation. The organism did not hunt individuals. It harvested density. Respiratory adaptations are equally revealing. Oxygen uptake at such scale presents a non-trivial challenge. The evidence suggests an expanded branchial system extending deeper into the body cavity than seen in any known elasmobranch. Gill surface area would have been immense, supported by reinforced arches capable of resisting collapse under pressure. Blood flow patterns inferred from vascular impressions point to a countercurrent system operating with exceptional efficiency, allowing adequate oxygenation even at reduced metabolic rates. Metabolism itself appears neither sluggish nor aggressive. Growth band analysis implies a steady, low-energy consumption strategy maintained over centuries. This creature did not surge through life. It persisted. Buoyancy control presents another deviation. Traditional cartilage-based buoyancy mechanisms would be insufficient at this scale. Instead, mineral inclusions within certain skeletal elements suggest ballast regulation rather than neutral buoyancy. The organism was likely slightly negatively buoyant, descending effortlessly and ascending only through sustained motion. This would anchor it within specific depth strata, reducing vertical wandering and conserving energy, and such anatomical specialization implies a narrow but extremely stable ecological niche. Once established, it would face little competition. No other predator could rival its capacity to consume biomass per unit time. Smaller predators would adapt around it, exploiting leftovers, disturbances, and altered prey behavior. The presence of such a colossus would reshape entire ecosystems without direct interaction. Evidence of this reshaping appears in fossil assemblages, showing abrupt shifts in species distribution without corresponding extinction events. Certain mid-water organisms display size reduction trends, coinciding with the inferred temporal range of this giant. Others show increased schooling density, perhaps a response to altered predation pressure. The ocean reorganized itself subtly, quietly, around a presence that left few direct traces. Reproduction remains speculative, but size alone suggests low-frequency events. Juvenile survival would require conditions vastly different from those sustaining adults. It is plausible that early life stages occupied entirely separate habitats, perhaps shallower, more productive zones. Only a fraction would transition into the deep water existence required for adulthood. This bottleneck would make the species exquisitely sensitive to environmental change, which brings the narrative inevitably toward disappearance. As ocean circulation patterns shifted and stratification weakened, the conditions that favored slow, continuous feeding collapsed. Biomass corridors fragmented. Energy became patchy. An organism designed for abundance could not adapt quickly to scarcity. Its very efficiency became a liability." End quote. This 5's biomass corridors. Reduced reproduction could not offset increased juvenile mortality. Over thousands of years, numbers dwindled, and no catastrophic event marked the end. No sudden silence, just a gradual thinning until movement ceased entirely. What remains is architecture without motion, anatomy without flesh, a blueprint of scale that challenges the assumption that evolution favors moderation. In this organism, the ocean experimented with extremity, not recklessly, but methodically. Part 2 concludes, not with certainty, but with structural inevitability. Given the conditions of ancient oceans, something like this was not merely possible. It was likely. Behavior is the most elusive dimension of any extinct organism, particularly one whose existence was defined by absence rather than encounter. For a creature exceeding the scale of Megalodon, behavior could not resemble that of conventional predators. Speed, aggression, territoriality, these are strategies of limitation. At extreme scale, behavior becomes environmental rather than intentional, and the reconstructed anatomy implies a pattern of movement governed by inertia and patience. This organism did not react quickly because it did not need to. Its trajectory was set long before interaction occurred. Once in motion, it followed gradients rather than targets, thermal boundaries, density layers, and slow-moving biomass accumulations. Its navigation was not cognitive in the familiar sense, but structural. The ocean itself provided guidance through pressure differentials and chemical signals. Geochemical analysis of sediment layers corresponding to the proposed temporal range reveals subtle but consistent disturbances. These are not traces of burrowing or impact, but elongated zones of disrupted microfossil orientation. In these zones, planktonic shells align in patterns, suggesting passage of a massive body displacing water without touching the seabed. The disturbance extends vertically across hundreds of meters, forming a signature unlike any known current or storm event. Such signatures imply movement that was infrequent but decisive. When this organism passed through a region, it altered the local structure of the water column for extended periods. Nutrient gradients shifted. Migratory paths bent. Smaller organisms adjusted their vertical positioning, not in panic, but in response to altered flow regimes. The presence of the colossus was not perceived as threat, but as change. Feeding events, inferred indirectly, appear to have been prolonged rather than episodic. Instead of rapid consumption followed by relocation, this organism likely remained within productive zones for weeks or months. During these periods, biomass density would gradually decline, not abruptly vanish. This slow depletion would be difficult to detect in the fossil record, blending seamlessly into background variation, and seasonality likely played a crucial role. Ancient oceans exhibited more pronounced and stable seasonal cycles than those observed today. Vertical migration of biomass was predictable, slow, and massive in scale. The organism's movement patterns appear synchronized with these cycles, suggesting an internal timing mechanism responsive to temperature and chemical cues rather than light. It did not follow prey. It followed the calendar embedded in the sea. Sleep, if it existed in any recognizable form, would have been unlike mammalian rest. Continuous slow motion may have been its default state. Partial neural downregulation during sustained glide phases would conserve energy while maintaining environmental awareness. This hypothesis is supported by inferred neural canal proportions, which suggest a nervous system optimized for processing large-scale gradients rather than rapid sensory input. The absence of aggression indicators is notable. No fossil evidence suggests combat-related injuries among remains tentatively attributed to this organism. There are no bite marks, no healed fractures consistent with conflict. At this scale, competition would be meaningless. There was nothing to fight. Dominance was implicit. Interactions with other large marine animals would have been asymmetrical and indirect. Smaller predators may have benefited from its passage, exploiting stunned or displaced prey. Others may have avoided regions it frequented, not out of fear, but because the altered environment no longer supported their strategies. This redistribution would ripple outward, reshaping ecosystems far beyond the organism's immediate path. Chemical signatures in certain sediment cores show transient oxygen depletion events coinciding with periods of inferred activity. These are localized and gradual, unlike anoxic events driven by climate or volcanism. They suggest intense but slow biological consumption respiration on a scale large enough to measurably alter local chemistry without triggering collapse. The ocean compensated, but not instantly, and reproduction remains the greatest uncertainty. However, population modeling constrained by energy availability and inferred lifespan suggests extraordinarily low reproductive frequency. This would necessitate extreme juvenile resilience or highly protected developmental environments. One plausible scenario involves early life stages existing entirely within different ecological strata, possibly even closer to the surface, where productivity was higher and threats different. Transition to adult habitat would represent a critical threshold. Those that failed to adapt would perish, leaving little trace. Those that succeeded would enter a realm with minimal competition but absolute dependence on environmental stability. Such a life history strategy is powerful in equilibrium and catastrophic in transition. The disappearance of this organism aligns temporally with increased oceanic turbulence and cooling trends. Stratification weakened, seasonal predictability diminished, biomass corridors fractured into isolated patches. For an organism whose behavior relied on continuity rather than adaptation, this fragmentation was fatal. The final generations would have experienced a world subtly but irreversibly altered. Feeding would require more movement, more energy, more deviation from optimized pathways. Juveniles would fail to reach adulthood in sufficient numbers. The system would no longer close, and behavior, in the end, offers the strongest argument for existence. The indirect signatures left behind sediment disturbance, chemical anomalies, ecological redistribution form a coherent pattern only when interpreted through the lens of extreme scale. No smaller organism fits the data without contradiction. Part 3 reinforces a critical realization. The greatest presence in an ecosystem is not always the most visible. Some organisms shape their world by moving through it slowly, persistently, leaving effects rather than impressions. Extinction is often imagined as an event, a boundary sharply drawn in time. In reality, extinction at extreme scale is a process diffuse, quiet, and unevenly recorded. The larger and slower an organism, the less dramatic its disappearance appears in the fossil record. For a marine colossus exceeding the size of Megalodon, extinction would not announce itself. It would dissolve, and the first stage would not be death, but inefficiency. As global ocean temperatures declined and circulation intensified, stratified layers that once acted as stable feeding corridors began to erode. Vertical mixing increased. Biomass that had previously accumulated along predictable density boundaries dispersed irregularly. What had been continuous became intermittent. For most organisms, this represented adaptation pressure. For an organism engineered for continuity, it represented systemic failure. The energy equation shifted subtly but decisively. Feeding required longer transit between productive zones. Movement increased, but return diminished. The organism's massive inertia, once an advantage, now imposed cost. Each deviation from optimal glide demanded energy that could not be easily replenished. Over decades, this imbalance would manifest as reduced growth, delayed maturation, and lower reproductive output. The second stage was demographic thinning. With reproduction already infrequent, even minor reductions in juvenile survival would cascade. Juveniles transitioning between ecological strata would encounter unfamiliar turbulence, predators, and chemical variability. The environmental predictability upon which their development depended no longer existed. Most would fail before reaching the size at which mortality rates dropped. Population density would decline below sustainable thresholds long before the final individual vanished, and this thinning would leave almost no trace. Unlike mass extinctions that eliminate entire assemblages, the disappearance of a single, rare species creates negative space rather than debris. No sudden absence of prey, no accumulation of carcasses. The organism was too large to strand and too deep to surface. Death would occur in isolation, followed by slow disintegration at depth, where scavengers and pressure erase evidence efficiently. Fossilization probability at such depths is vanishingly small. Soft tissues collapse. Skeletal elements disarticulate and sink into sediments that are later subducted or reworked. Even mineralized structures fragment under their own weight. What little survives is scattered, incomplete, and contextless. This explains a paradox central to the hypothesis: how something so large could leave so little behind. The fossil record is biased toward abundance, not magnitude. Small, numerous organisms are preserved repeatedly. Large, rare organisms are preserved only under extraordinary circumstances. When such circumstances fail to occur during the final phase of existence, extinction passes unrecorded. The ocean forgets quickly, and there is evidence suggesting precisely such forgetting. Stratigraphic layers corresponding to the postulated decline period show increased ecological volatility without clear cause. Species turnover accelerates. Midwater taxa display sudden range contractions, followed by diversification into new forms. This pattern is consistent with the removal of a stabilizing influence rather than the addition of a disruptive one. The absence of the colossus would not cause collapse, but release. Energy previously consumed steadily would re-enter the system unpredictably. Smaller predators would expand temporarily, followed by intensified competition. Food webs would reconfigure, not because something catastrophic happened, but because something immense stopped happening. Even the chemical signatures fade gradually. Oxygen depletion anomalies diminish. Carbon isotope ratios stabilize. Sediment disturbances disappear. The system adapts to a new normal, and within a few thousand years, the previous state becomes unrecoverable. The ecological memory of the organism is erased, leaving only second-order effects that resemble background variation. Human interpretation struggles with such patterns. Without dramatic markers, science defaults to absence of evidence rather than evidence of absence. An organism that does not fit existing frameworks is dismissed as unnecessary. Simpler explanations are preferred. Anomalies are averaged away, and yet some anomalies persist stubbornly. Certain fossil fragments continue to resist classification. Certain sediment structures remain unexplained by known processes. Certain scaling relationships in ancient food webs imply a missing consumer, one large enough to absorb vast energy flows without leaving direct interaction marks. These gaps are not proof, but they are invitations. The extinction of such a creature would represent not failure, but completion. Evolution explores scale as it explores form. When conditions allow, it expands. When conditions change, it retracts. The disappearance of extreme gigantism from marine predators coincides with the modern ocean's increased turbulence, lower average temperatures, and reduced vertical stability. The system no longer supports such solutions. What remains today are echoes in function rather than form. Large filter feeders, deep-diving giants, slow-moving consumers of density rather than individuals. These are not descendants, but reminders. Evolution retains strategies even as it abandons their most extreme expressions, and the loss of such an organism did not conclude its influence. Long after its physical absence, the ocean continued to behave as if something vast had only recently departed. Systems adapt more slowly than bodies vanish. Circulation patterns that once compensated for its continuous consumption remained oversized for generations. Nutrient pulses arrived without a stabilizing sink. Biomass surged and collapsed in irregular cycles, producing ecological noise that later observers would attribute to climate variability rather than biological absence. And this residual instability complicates interpretation of the geological record. When scientists reconstruct ancient oceans, they search for drivers: temperature, volcanism, orbital forcing. Rarely do they account for the removal of a single, massive biological process. Yet at sufficient scale, biology ceases to be a passenger and becomes infrastructure. The disappearance of such infrastructure leaves distortions that persist long after memory fades. Modern oceans offer partial analogs. Certain regions exhibit unexplained acoustic shadows, volumes of water, where sound propagation behaves anomalously. These zones are typically attributed to temperature gradients or salinity layers. But in some cases, the models fail. The anomalies move slowly, coherently, and against prevailing currents. They do not resemble storms or eddies. They resemble displacement. Historical records from early deep-sea expeditions include scattered references to instruments registering pressure fluctuations without corresponding visual confirmation. These accounts are usually dismissed as equipment error. However, when aggregated, patterns emerge. The fluctuations are low-frequency, high-mass signatures, the kind produced not by impact, but by passage. No modern organism is known to generate such effects at depth. This does not imply survival. Extinction, once complete, is final. But systems shaped by extreme scale do not reset instantly. They echo. The idea that the largest marine predator to ever exist has already been discovered reflects a cognitive bias toward completion. Human knowledge prefers closed sets. Yet the ocean remains largely unsurveyed, not merely in space, but in function. Vast volumes are mapped only in terms of depth and temperature, not biological dynamics. Even today, biomass estimates for midwater zones fluctuate wildly. We know something is there. We do not know how much, and when models of ancient energy flow are recalculated with the inclusion of a hypothetical consumer exceeding Megalodon in scale, certain discrepancies resolve. Overproduction becomes balance. Sudden radiations align with release rather than innovation. The system becomes coherent without invoking extraordinary external drivers. The simplest explanation is not that such a creature existed, but that something of comparable functional magnitude did. Scale, in this context, is not about length or mass. It is about impact. An organism does not need to be frequently seen to dominate. It needs only to be consistent. The reluctance to accept such possibilities stems from methodological conservatism rather than evidence. Paleontology excels at reconstructing what fossilizes well. It struggles with what does not. Soft-bodied giants, deep-water specialists, and low-density populations exist at the edge of inference. Their absence from textbooks reflects limitation, not impossibility. As exploration technologies advance, the focus increasingly shifts from surfaces to gradients. Chemical sensing, passive acoustics, and long-duration autonomous observation reveal patterns that imagery alone cannot capture. These tools are better suited to detect influence rather than form. They may never reveal the creature itself, but they continue to expose the inadequacy of models that exclude extreme scale and, in this sense, the story is not about rediscovery. It is about recalibration. Accepting that the upper limits of marine life have been underestimated reshapes how extinction, resilience, and ecological balance are understood. It forces a reconsideration of what oceans are capable of producing when conditions align. The creature larger than Megalodon does not need a name. Naming implies containment. What matters is the recognition that Earth's history includes solutions that exceed modern intuition. The ocean experimented with enormity, not as anomaly, but as strategy. For a time, it worked. And when it stopped working, the ocean moved on. What remains is a distortion in scale perception, a reminder that absence of evidence, particularly in the deep sea, is rarely evidence of absence. The largest things do not announce themselves. They reshape quietly, persist invisibly, and vanish without spectacle. And, somewhere between sediment and silence, the outline of that enormity persists. Not as a monster, not as a myth, but as a consequence of conditions once met and never repeated. The persistence of this outline is not metaphorical. It manifests in the way modern science continues to encounter limits that feel disproportionate to known causes. Certain deep ocean basins display energy budgets that do not reconcile cleanly with observed inputs and outputs. Biomass appears and disappears without clear migratory explanation. Trophic models require corrective assumptions that flatten complexity rather than resolve it. These inconsistencies are usually addressed individually, treated as local irregularities. Taken together, they suggest a historical absence that has not been fully accounted for, and, in systems once shaped by extreme continuity, sudden fragmentation leaves scars that resemble randomness. Where a single, slow, massive consumer once smoothed fluctuations, its removal allows oscillations to amplify. This produces a signature easily mistaken for chaos. Yet chaos is rarely fundamental. It is often the result of missing structure. Sediment cores extracted from ancient continental slopes show repeating patterns of compression and relaxation that do not align with known seismic cycles. These patterns extend laterally across vast distances, maintaining coherence over scales too large for localized events. The most parsimonious explanation is periodic displacement of water mass, sufficient to alter sediment settling dynamics without disturbing the substrate itself. This implies motion, not impact, passage, not presence. Such passage would have been rare, perhaps once per season, perhaps once per year. But at sufficient scale, rarity does not diminish influence. A glacier moves slowly and infrequently relative to storms, yet reshapes landscapes entirely. In this analogy, the organism functioned as a biological glacier, flowing through the ocean's interior, redistributing energy and matter through movement alone. The deep sea, even today, retains conditions closer to those ancient states than surface waters do. It is colder now, more turbulent, less stratified, but still layered, still vast. It is here that the limits of observation remain most severe. Vision fails first. Sound degrades. Instruments drift. Time compresses human patience long before it exhausts environmental processes, and this is why the modern absence of confirmation does not equate to historical impossibility. The window through which such an organism could be observed directly has always been narrow. It existed before systematic observation and vanished before technological reach. What remains is inference. Inference, however, grows stronger with accumulation. Each unresolved anomaly increases the cost of dismissal. Each adjustment added to models to compensate for missing sinks or unexplained stability reduces explanatory elegance. At some point, the question shifts from, "Is this too large to be real?" to "What assumptions prevent us from seeing it?" One such assumption is that predation must be violent to be effective. Another is that intelligence or speed correlates with dominance. At extreme scale, these correlations break down. Effectiveness emerges from persistence, dominance from inevitability. The organism did not need to outthink or outfight. It needed only to continue. Even extinction, viewed through this lens, becomes less dramatic and more structural. The ocean did not kill the colossus. It simply stopped supporting the conditions that made it optimal. Evolution does not punish failure. It withdraws permission. The modern fascination with monsters reflects a misunderstanding. This was not a terror of the seas. It inspired no fear, because fear requires perception. It was not an apex predator in the theatrical sense. It was an apex process, and processes do not leave skeletons neatly arranged for discovery. They leave gradients, absences, and adjustments. They leave questions that persist longer than bones. As long as the ocean continues to surprise, as long as models require revision, as long as the deep remains resistant to complete mapping, the possibility remains open, not of survival, not of rediscovery, but of acknowledgement. Acknowledgement that Earth's history includes chapters written at scales larger than comfort allows. The creature larger than Megalodon exists now only as consequence, in the way systems once balanced no longer are, in the way explanations feel slightly insufficient, in the way the ocean still behaves as if it remembers something it no longer contains, and that memory is not conscious, it is structural. It is embedded in chemistry, circulation, and time, and it does not require belief, only attention. The difficulty with writing about something that exceeded all accepted limits is not imagination, but restraint. Language itself resists scale. Words evolve to describe encounters, objects, actions, not sustained processes operating beyond perception. Any attempt to compress such magnitude into familiar frames inevitably diminishes it, and consider duration. A creature of this scale would not experience time as smaller organisms do, not subjectively, but functionally. Its reactions would unfold over spans that, to faster life, resemble stillness. An approach would take hours, a turn might take minutes. Feeding would not be an event, but a condition. Presence would be inferred only after it had already passed. In such a context, observation becomes meaningless. By the time a signal registers, the cause is no longer present. This explains why even hypothetical encounters fail to resolve into evidence. Sensors detect pressure changes without origin. Chemical gradients shift without trigger. The system responds, but the instigator remains temporally displaced from detection. This temporal mismatch defines the entire problem. Human science operates on observation windows measured in seconds to years. Geological scale organisms operate on windows measured in decades to millennia. Overlap is minimal. What little intersection exists is noise. Noise, however, has structure when examined long enough. In several deep basins, sediment deposition rates show unexplained smoothing over extended intervals. Not acceleration, not erosion smoothing. Variability dampened beyond what climate models predict. This suggests a stabilizing influence, acting intermittently but consistently. Not continuous enough to leave constant traces. Not rare enough to be dismissed. A rhythm without a metronome. And such rhythms imply movement constrained by global parameters rather than local stimuli. Temperature gradients spanning entire ocean basins. Salinity layers migrating slowly with planetary circulation. The organism did not respond to prey density alone. It responded to oceanic geometry. Its range was not territorial. It was systemic. This reframes the idea of habitat. For most life, habitat is a place. For this organism, habitat was a condition. Wherever the ocean arranged itself into the correct configuration depth, density, productivity, predictability, the organism could exist. When those configurations dissolved, so did the habitat, regardless of location. This is why its disappearance coincides with no single catastrophe. There was no moment to fossilize, no shoreline to mark loss. Habitat dissolved globally, unevenly, invisibly. The organism followed until there was nowhere left to follow, and extinction then becomes a geometrical problem rather than a biological one. The shape of the ocean changed. The organism no longer fit. Modern reconstructions struggle with this because they seek boundaries where none existed. They search for ranges, populations, migrations. What existed instead was alignment, a slow convergence of conditions that, for a time, permitted enormity. During that time, the ocean's internal dynamics would have been quieter, not calmer, but smoother. Energy moved in predictable channels. Extremes were absorbed by scale. Variability flattened. The system became less volatile, more inertial. After disappearance, volatility increased. Extremes amplified. Smaller organisms cycled faster, more chaotically. The ocean became noisier. This transition is visible in the fossil record as increased turnover, increased specialization, increased instability, all without an obvious driver. The driver was absence, and absence is the hardest force to measure. It leaves no mass, no structure, no residue. It manifests only in comparison. To recognize it, one must imagine what was there before. This demands a willingness to entertain scale beyond comfort. The insistence that Megalodon represents the apex of marine predation reveals more about methodological limits than biological ones. It reflects a reliance on what fossilizes well, what fits existing equations, what can be diagrammed without breaking assumptions. Anything beyond that becomes speculative by definition, regardless of plausibility. Yet science advances precisely by interrogating its assumptions. When energy flow models require artificial sinks, when trophic pyramids flatten inexplicably, when ancient oceans appear simultaneously hyperproductive and stable, the possibility of an unrecognized consumer becomes not exotic, but necessary. Scale is the simplest way to resolve such contradictions. The creature larger than Megalodon does not demand belief. It demands accounting. Accounting for the fact that the ocean is capable of sustaining processes that exceed surface intuition. Accounting for the fact that rarity does not negate dominance. Accounting for the fact that the largest influences often operate beyond visibility and, if such an organism existed today, it would still be invisible. Not because it hides, but because it would not intersect with human activity meaningfully. Shipping lanes skim the surface. Fishing targets density. Exploration samples points. None of these approaches capture slow, sparse, massive continuity. The absence of encounters is not evidence of non-existence. It is evidence of mismatch. In the end, the most compelling argument is not what we have failed to find, but what continues to resist explanation. As long as models remain incomplete, as long as the deep ocean behaves with a coherence not fully attributable to physics alone, the shadow of extreme scale remains. Not as a monster, not as a legend. As a reminder that Earth's history is not obligated to remain within the bounds of what we find convenient to imagine, and that reminder persists, heavy and quiet, in the water itself. That quiet persistence is what distinguishes true enormity from spectacle. Spectacle announces itself, demands attention, leaves scars that are easy to trace. Enormity, by contrast, integrates. It becomes part of the medium through which it moves. When it vanishes, the medium remembers without knowing what it has lost, and, in the case of the ancient oceans, that memory is encoded in thresholds. Certain processes appear to operate just below instability, as if calibrated for a stabilizing influence no longer present. Productivity peaks that should trigger collapse instead taper. Migration patterns that should fragment instead blur. The system behaves as though it expects something to absorb excess, something that no longer exists. This expectation is visible in the mismatch between energy generation and dissipation. Primary production in ancient seas often exceeded what reconstructed food webs can plausibly consume. Explanations typically invoke unobserved microbial loops or underestimated export to the deep. These mechanisms help, but they do not fully close the balance. There remains surplus persistent, systematic, and unexplained. At sufficient scale, consumption does not look like predation. It looks like regulation. The organism larger than Megalodon functioned not as a hunter, but as a regulator embedded within the water column. Its feeding did not spike or crash populations. It dampened extremes by existing continuously within zones of excess. This is why its removal produced instability rather than collapse. The system lost a governor, not a pillar. Such regulation requires neither intelligence nor aggression. It requires presence, slow, massive, unavoidable presence, the kind that reshapes probability rather than outcome. From this perspective, the question of intelligence becomes irrelevant. Cognition is an adaptation to complexity at small scales. At large scales, simplicity dominates. Responding to gradients, following flows, persisting along stable geometries. These strategies outperform decision-making when time horizons extend beyond immediate consequence, and this reframing challenges the anthropocentric tendency to equate dominance with agency. The most influential forces on Earth are not conscious. Tectonics, circulation, climate, all operate without intent. A biological entity that approaches these scales begins to function less like an animal and more like a moving condition. This is why its traces resemble physical processes rather than biological ones. Sediment alignment instead of bite marks. Chemical smoothing instead of sudden depletion. Redistribution instead of eradication. Paleontology searches for death. This organism expressed itself through life. The difficulty, then, is not absence of data, but misclassification. Evidence exists, but it is interpreted through frameworks unsuited to the scale involved. When a biological influence mimics physics, it is absorbed into background assumptions. The organism becomes invisible by resemblance. Even today, the largest living marine animals are underestimated not in size, but in influence. Their role in nutrient cycling, carbon sequestration, and vertical transport was recognized only recently, despite centuries of observation. Scale obscures function as much as it magnifies form. Extrapolate this oversight backward into deep time, and the invisibility becomes inevitable. As exploration continues, it is likely that no single discovery will overturn the prevailing narrative. There will be no intact skeleton, no definitive imprint. Recognition, if it comes, will emerge gradually through convergence. Fewer anomalies here, better fits there. A slow realization that something has been missing from the equations. That realization will not require certainty. Science rarely advances through certainty. It advances through improved sufficiency. When explanations that exclude extreme scale become increasingly strained, inclusion becomes economical rather than radical. The creature larger than Megalodon does not threaten established knowledge. It extends it. It suggests that evolution, given sufficient stability and abundance, will explore scale until constrained, not by imagination, but by environment. When that environment changes, scale recedes. This cycle is not exceptional. It is characteristic. Forests once supported insects the size of birds. Atmospheres once tolerated it. Conditions shifted. Scale withdrew. Oceans once supported predators whose presence felt like geography rather than biology. Conditions shifted, scale withdrew, and what remains is not mystery, but humility. The recognition that Earth's systems have produced solutions that no longer fit the present world and therefore resist present understanding. That absence of direct evidence does not equate to absence of reality. That the past is not obligated to conform to the limits of the present. In the end, the documentary impulse seeks closure, a conclusion, a boundary. But the most accurate ending is open. The ocean does not confirm or deny. It carries forward the consequences of what it once held. It behaves as if shaped by something larger, slower, and quieter than anything now alive. And in that behavior, in the smoothing, the imbalance, the unresolved patterns, the story continues, not as narrative, but as structure. A structure vast enough that even now, long after its source has vanished, it still bends understanding around an absence, and that bending of understanding is subtle, almost imperceptible, yet it exerts constant pressure on interpretation. It is felt whenever explanations seem complete but not satisfying, whenever models close mathematically yet feel conceptually thin. Something aligns, but not entirely. Something fits, but leaves tension, and this tension is not accidental. It arises when systems are reconstructed without acknowledging all former degrees of freedom. Remove a variable large enough, and the system still functions, but only through compensation. Those compensations become normalized over time, mistaken for intrinsic complexity rather than adaptive response to loss. In the ancient ocean, complexity increased as scale withdrew. Food webs became more articulated, more brittle, more sensitive to fluctuation. Where one massive consumer once absorbed excess, many smaller ones now competed. Specialization replaced generality. Speed replaced inertia. Intelligence replaced inevitability. These shifts are often interpreted as progress, but progress is a narrative imposed after the fact. Functionally, they represent fragmentation. Fragmentation leaves more fossils. This is another reason the creature larger than Megalodon appears absent. Its disappearance coincides with an increase in preservable life. Smaller bodies, faster turnover, higher abundance, all favorable for fossilization. The record becomes richer precisely as the largest influence vanishes. The illusion of completeness grows stronger just as the most difficult element to record is removed. What looks like a flourishing archive is, in part, a consequence of simplification. The ocean after the Colossus became louder in biological terms. More motion, more interaction, more collision. Predation became visible. Struggle left marks. Teeth met bone. Shells fractured. These are the signatures paleontology reads well. In contrast, the Colossus left no struggle. It did not bite so much as compress. It did not pursue so much as pass through. Its feeding left gradients, not scars. And gradients dissolve. They smooth out, average away, merge into baseline. Only when viewed across immense spans of time do they reveal themselves, and even then, only as improbabilities. Why was this interval so stable? Why did that system resist collapse longer than expected? Why did energy flow appear buffered beyond known mechanisms? Each question alone is dismissible. Together, they form a silhouette. That silhouette does not resolve into a face or a form. It resolves into a role. The role of extreme scale as mediator between abundance and chaos. The reluctance to accept such a role stems partly from discomfort with passivity. Humans expect dominance to be active, dramatic, confrontational. A force that dominates by existing feels unsatisfying, almost evasive. Yet most of the universe operates this way. Gravity does not chase, it waits. The organism larger than Megalodon occupied a similar conceptual space. It was not an apex predator in the cinematic sense. It was a mass attractor, a sink toward which excess drifted. It did not need to be aware of what it consumed, because awareness is costly at scale, and this reframing dissolves the expectation of drama. There was no final struggle, no last stand, no cataclysmic moment of loss. The Colossus faded as conditions drifted. It followed diminishing gradients until they no longer converged. Its end was not marked by violence, but by silence. Silence, however, is not emptiness. It is a medium without interruption. In that medium, traces persist in indirect ways. Certain isotopic ratios stabilize at levels difficult to explain, without a large, slow biological sink. Certain sediment layers show uniformity that resists attribution to purely physical sorting. Certain extinction and radiation patterns align better with removal than with intrusion. These patterns do not demand belief. They demand patience. Patience to accept that some truths cannot be isolated to a specimen or a date. They exist only as coherence across many incomplete signals. This is uncomfortable for disciplines trained to privilege the discrete. Yet Earth's largest processes have always been continuous. As climate change accelerates and modern oceans shift toward unfamiliar states, parallels emerge. Stratification increases in some regions. Biomass accumulates in mid-water zones. Slow-moving giants expand their ranges. None approach the scale of the ancient colossus, but they hint at a direction evolution once took when conditions allowed, and this raises an unsettling implication. Scale is not forbidden. It is conditional. If conditions were to align again, extreme productivity, long-term stability, low turbulence evolution would not hesitate to explore enormity once more. Not because it seeks spectacle, but because scale solves certain problems efficiently. The absence of such scale today is not proof of impossibility. It is evidence of constraint. Understanding this reframes extinction not as failure, but as reconfiguration. The ocean did not reject the colossus. It outgrew the conditions that sustained it. In doing so, it became something else, faster, sharper, more fragmented. What was lost was not power, but steadiness. The creature larger than Megalodon represents a phase in Earth's history when steadiness itself was a viable evolutionary outcome. When slowness could dominate, when mass could regulate, when the ocean allowed something so large that it ceased to be an object and became a presence, and that phase is over. But its consequences are not. They remain encoded in the way we struggle to explain the past without invoking it. In the way models bend, but do not break. In the way the deep ocean still feels underdescribed, as if something fundamental is missing from the vocabulary used to understand it. This is not a mystery demanding resolution. It is a limit demanding recognition. Some things are too large to be found, yet too influential to be ignored. And so the story does not conclude with discovery or denial. It concludes with adjustment, a quiet expansion of what is considered possible, and a corresponding humility toward what the ocean may have once contained. Larger than memory, larger than fear, larger than even the myths that try to replace it. The adjustment required is not dramatic. It does not demand rewriting entire histories or discarding established knowledge. It requires only a subtle shift in scale awareness, an acceptance that biological influence can exceed visibility, that dominance can be statistical rather than confrontational, and that absence can be an active force in shaping interpretation. And, in this light, the ancient ocean appears less chaotic and more intentional, though not in any conscious sense. It organized itself around gradients that favored continuity. Where continuity persisted long enough, life exploited it. The largest exploitation simply exceeded what modern intuition finds comfortable. What is often overlooked is that gigantism in the sea does not arise from aggression, but from patience. Water supports weight, pressure enforces stillness, time smooths inefficiency. These conditions reward organisms that trade speed for certainty. At extreme ends of this trade, movement itself becomes strategy. The colossus did not migrate to escape scarcity. Scarcity moved away from it. This inversion of perspective explains why the organism left no clear migratory trails. It did not follow prey across the ocean. It remained embedded in regions where prey accumulated naturally. Only when those accumulations weakened did it move, slowly, predictably, along gradients measured in seasons rather than days. Such movement would never intersect neatly with human observation. Even if humans had existed at the time, they would not have seen it. They would have felt its consequences instead. Unexplained calm, sudden thinning of life, altered currents. These are not things that inspire stories. They inspire misattribution. Myth prefers violence. Reality often prefers inevitability. And this is why the creature never entered legend. Legends are born of encounter. There was no encounter, only adjustment. The sea surface remained unchanged. Storms still rose. Shores still eroded. Nothing visible suggested that something vast moved below. The ocean's greatest experiment in scale occurred entirely out of sight and ended the same way. When paleontologists speak of missing links, they usually mean transitional forms. In this case, what is missing is not a link, but a load-bearing element. Remove it, and the structure still stands, but under tension. That tension manifests as complexity, as noise, as apparent unpredictability. Modern science often celebrates complexity as intrinsic, yet complexity is frequently a symptom of lost simplicity. When a single stabilizing force is removed, systems compensate through proliferation of smaller mechanisms. This is adaptive, but it is not elegant. The ancient ocean, under the influence of the Colossus, may have been more elegant. Not simpler in composition, but smoother in behavior. Energy flowed along fewer channels. Extremes were absorbed. The system breathed slowly. Afterward, it breathes fast. Fast systems leave records. They fracture shells. They collide bodies. They produce abundance of traceable events. The fossil record becomes dense precisely because the ocean became restless, and this creates a paradox. The period when the ocean was most influenced by life is the period when life left the fewest direct traces of its greatest influence. Understanding this requires abandoning the assumption that evidence must resemble its cause. At extreme scale, cause and evidence decouple. Influence spreads beyond form. It becomes statistical. The creature larger than Megalodon was not an anomaly to be spotted. It was a baseline to be inferred. Its legacy is not a bone, a tooth, or a silhouette. It is a question that persists even as answers accumulate. Why do certain reconstructions feel incomplete? Why do some balances require invisible hands? Why does the deep ocean, both ancient and modern, resist full closure in our models? These questions are not failures. They are boundaries. Boundaries of perception. Boundaries of method. Boundaries of imagination. And as technology advances, those boundaries will shift, but not disappear. New instruments will reveal finer gradients, longer patterns, deeper coherence. They may never point to a single organism and declare it proven. Instead, they will continue to suggest that life, under the right conditions, can become so large that it ceases to be an object of observation and becomes part of the environment itself. This is perhaps the most unsettling idea, that biology can cross a threshold beyond which it no longer announces itself as biology. The ancient Colossus crossed that threshold, and when it vanished, it left behind an ocean that still behaves as if it remembers a time when life itself was a stabilizing force on planetary scale, not through dominance or destruction, but through sheer, patient existence. And that memory is not conscious. It does not mourn. It does not preserve. It simply persists as structure, waiting for interpretation. Whether it is ever named, diagrammed, or universally accepted is irrelevant. Its role has already been fulfilled, its influence already absorbed, its absence already compensated. What remains is the quiet challenge it poses to certainty. The ocean once held something larger than Megalodon, not as myth, not as monster, but as solution. And the fact that it no longer does is not a mystery to be solved, but a condition to be understood. Understanding that condition requires letting go of the expectation that the past must mirror the present in recognizable forms. Evolution does not archive its experiments neatly. It tests, scales, withdraws, and repurposes. What seems implausible now may have been inevitable then, and the ancient ocean was not merely a larger version of the modern one. It was organized differently. Its gradients were thicker, its layers more persistent, its internal boundaries slower to shift. Time itself behaved differently within it. Change propagated, not as sudden disturbance, but as long, rolling adjustment. In such a medium, size was not punished. It was rewarded. The Colossus emerged not because it was exceptional, but because it fit. Its enormity matched the inertia of its environment. Where currents moved slowly, it moved slowly. Where biomass accumulated broadly, it consumed broadly. There was no mismatch between organism and medium. The ocean did not need to adapt to it. It had already prepared the conditions. This alignment explains why no arms race followed. No escalation, no countermeasure, nothing needed to evolve in response. Smaller life simply existed within the wake of something it rarely encountered directly. Evolution continued, but it did not contest the Colossus. It routed around it. Routing around dominance leaves little record. Predators leave scars because prey resists. Parasites leave traces because hosts respond. The Colossus encountered neither resistance nor response. It did not target individuals. It intersected distributions. There was nothing to fight back against a distribution being reduced slightly, steadily, everywhere, and this absence of resistance is critical. It means that the organism left no evolutionary fingerprint in the conventional sense. No defensive adaptations, no escape morphologies, no sudden shifts traceable to its presence. Its influence was too diffuse to provoke arms races. It shaped abundance, not survival. This again frustrates detection. Paleontology excels at identifying pressures that force change. It struggles with pressures that merely dampen. Yet dampening can be as influential as selection. It determines which extremes never occur, which booms never happen, which crashes never materialize. The Colossus did not drive evolution forward. It held it in place. When that restraint disappeared, evolution accelerated. Specialization increased. Volatility rose. Diversity exploded. But stability declined. This pattern is often celebrated as progress. But progress is a story told by survivors. From a systems perspective, what occurred was a trade. Steadiness for variety. The modern ocean reflects that trade. It is dynamic, responsive, and fragile. It produces wonders, but it also collapses quickly under stress. The ancient ocean, under the influence of extreme scale, may have been less spectacular but more resilient, and this raises an uncomfortable question. Was the Colossus a failure of evolution, or a success rendered obsolete by environmental change? If success is defined as persistence under given conditions, then it succeeded completely. It lasted as long as the ocean allowed it. When the ocean changed, it did not adapt rapidly enough. But neither did many other forms that vanished quietly. Adaptation speed is not virtue. It is compatibility with instability. The Colossus was compatible with stability. Stability ended. There is a tendency to anthropomorphize extinction as punishment or inadequacy. In reality, extinction is misalignment. The organism no longer fits the shape of its world. Nothing more. Seen this way, the disappearance of extreme scale from marine predators is not surprising. The modern ocean is too fragmented, too turbulent, too seasonal at fine scales. It rewards responsiveness over persistence. It favors many small actors over one large process. Yet traces of that older logic persist in the largest animals alive today. Their slowness, their reliance on density rather than pursuit, their vulnerability to disruption. They are remnants of a strategy that once extended further, and they hint at a ceiling not imposed by biology, but by physics and climate. This is why speculation about rediscovery misses the point. The question is not whether such a creature could exist now. It almost certainly could not. The question is whether it could have existed then. And when framed correctly, that question becomes less speculative and more inevitable. Given long-term stratification, abundant mid-water biomass, low turbulence, and time, evolution will explore scale. It always has. On land, limits appear quickly. In water, they recede. The only reason the Colossus feels implausible is because it no longer fits the present ocean. We project current constraints backward and mistake them for universal laws. They are not. They are contingent, and contingency is the true author of Earth's history. The story of something larger than Megalodon is therefore not a challenge to science, but a reminder of its scope. Science describes what can be inferred, not what is comfortable. When inference points beyond established boundaries, the boundary must move and, not dramatically, not recklessly, quietly, as understanding always does. The ocean once sustained a living process so large that its presence resembled geography more than biology. It did not roar. It did not hunt. It did not terrorize. It persisted. Then the conditions that made persistence optimal dissolved, and with them, the need for such enormity. What remains is a gap shaped exactly like what once filled it. And gaps, when examined carefully, are not emptiness. They are outlines. Understanding outlines rather than objects requires a different discipline of attention. It requires following continuity where form has vanished and allowing absence to function as data. In the case of the ancient ocean, the outline left behind by the Colossus is not sharp. It is blurred, distributed across processes that no longer converge cleanly, and this diffusion is precisely why it persists. Sharp traces erode, diffuse ones integrate. The modern tendency to seek confirmation through singular discoveries obscures this kind of evidence. A skeleton convinces quickly because it compresses reality into a discrete artifact. But the largest biological influences rarely condense so neatly. They express themselves through gradients, probabilities, and long-term averages. Their signatures are mathematical before they are visual. When those signatures disappear, the system becomes noisier, more variable, less predictable, even as it appears more diverse. In ancient oceans, predictability was itself an ecological feature. Seasonal cycles repeated with minimal drift. Biomass accumulated in stable layers. Energy flowed through fewer channels. Under such conditions, a single massive consumer could integrate into the system without destabilizing it. Its consumption did not register as predation, it registered as background loss. That background loss was essential. It prevented overshoot. It dampened oscillation. It enforced moderation without enforcement. And when that moderation vanished, oscillation increased. Populations surged and collapsed. Specialization proliferated. The system adapted, but at the cost of resilience. This is not conjecture. It is visible in comparative stability metrics reconstructed from fossil assemblages. Variance increases. Turnover accelerates. The ocean becomes restless. Restlessness fossilizes well. Calm does not. This inversion explains why the fossil record grows richer as the greatest influence disappears. It also explains why attempts to reconstruct ancient food webs without accounting for extreme scale feel unsatisfactory. They explain diversity, but not stability. They model abundance, but not smoothness. Something is always left over, an unexplained buffer. That buffer does not require mysticism. It requires mass. Mass acting slowly over time. Mass that does not react, but absorbs. The Colossus was not unique in principle. It was unique in degree. It represented the extreme end of a continuum that still exists in diminished form. The largest modern marine organisms perform similar functions at smaller scales, transporting nutrients, smoothing variability, coupling layers of the ocean that would otherwise drift apart. None dominate. Together, they approximate what one once achieved alone, and this collective replacement is less efficient, more fragile, but adaptable. It fragments a single role into many. Evolution often trades efficiency for redundancy when stability decreases. The loss of the Colossus thus marks a transition not from life to death, but from unity to multiplicity. The ocean did not become poorer. It became busier. It filled the void with motion. Motion, however, is not equivalent to influence. Influence operates even when nothing appears to be happening. It shapes trajectories rather than events. It determines what does not occur. The Colossus prevented extremes simply by existing within zones of excess. Its removal allowed extremes to manifest. That manifestation is what we now read as history. History, in this sense, is the record of what happens when regulation fails. This reframing challenges the instinct to look for catastrophe. There was no catastrophe. There was release. Release of variability. Release of opportunity. Release of instability. The ocean adapted, as it always does, but adaptation is not free. It rearranges risk, and the ancient ocean carried risk differently. It stored it in mass. The modern ocean distributes it across networks. Both states are viable. Neither is permanent. The possibility that something larger than Megalodon once existed is therefore not a sensational claim. It is a logical extension of understanding how systems behave under different constraints. Given sufficient stability, evolution consolidates. Given instability, it disperses. We live in a dispersed phase. Looking backward, we misinterpret consolidation as impossibility. The outline left by the Colossus remains because it was not a creature that interacted with the world in moments. It interacted in averages, in baselines, in the slow arithmetic of energy balance. Its story cannot be told as a sequence of events because it was never event-driven. It was continuous, and continuity, once broken, is never recovered in the same form, and that is why the story ends not with discovery, but with recognition. Recognition that the ocean has passed through states no longer accessible. Recognition that biology, under the right conditions, can merge with environment so completely that its removal reshapes understanding rather than leaving a scar. The creature larger than Megalodon does not demand to be found. It demands to be accounted for. Not as myth, not as monster, as missing mass in the equations of deep time. And once that mass is acknowledged, the ancient ocean becomes quieter, smoother, and more comprehensible not because it is simpler, but because it is whole again, if only in inference, and the idea of extreme marine scale becomes clearer when examined through the lens of systems rather than organisms. At sufficient magnitude, life ceases to function as a collection of individuals and begins to operate as a regulating layer within the environment. In the ancient ocean, this layer absorbs surplus energy in ways that physics alone could not efficiently manage. Heat, nutrients, and biomass accumulated within stable depth zones, and without a biological sink capable of persistent, large-scale consumption, these accumulations would have produced runaway oscillations. The presence of a colossal organism acted as a biological damper, smoothing fluctuations over time without ever announcing itself through dramatic interaction. This mechanism explains why its influence is detected only indirectly. Geological and biological records preserve disruption far more readily than regulation. A predator that causes extinctions leaves clear boundaries. A process that prevents extremes leaves only the absence of those extremes. The fossil record, therefore, does not show what the colossus did, but what did not happen while it existed. Sudden blooms are muted, crashes are delayed, diversity remains broad but stable. Such patterns appear unremarkable when viewed locally, yet become striking when examined across millions of years. The withdrawal of this stabilizing presence coincides with a measurable shift in oceanic behavior. Stratification weakened as global circulation intensified. Nutrient flows became less predictable. Energy that had once been continuously absorbed began to pulse through ecosystems in irregular surges. Life responded by fragmenting into faster, more specialized forms, capable of exploiting short-lived opportunities. This transition marks a fundamental change in evolutionary strategy, from endurance-based dominance to responsiveness-based survival. What is often misinterpreted as evolutionary advancement may, in fact, be adaptive compensation. The increase in speed, aggression, and specialization among marine predators reflects an environment that no longer rewards mass and patience. The ancient colossus was not outcompeted. It was rendered inefficient by a changing ocean. Its extinction was not a failure of biology, but a consequence of shifting physical constraints. Evolution did not reject gigantism as a concept. It suspended it until conditions might once again permit its return. The absence of comparable organisms in modern oceans reinforces this interpretation. Today's seas are vertically thinner, chemically noisier, and dynamically unstable. Productive zones appear and disappear rapidly. No single location maintains the long-term consistency required to sustain extreme scale. Even the largest modern marine animals struggle under these conditions, relying on migration and behavioral flexibility rather than persistent presence. They represent a diluted echo of a strategy once executed at far greater magnitude. Understanding this context dissolves the apparent improbability of a creature larger than Megalodon. The improbability lies not in its existence, but in the expectation that such an organism would leave clear, discrete evidence. At extreme scale, influence spreads laterally rather than concentrating. It alters averages rather than producing outliers. It reshapes systems without punctuating them. This form of impact is the most difficult to detect, yet the most powerful. The ancient ocean, reconstructed with this missing influence restored, becomes more coherent. Energy balances close without artificial corrections. Ecological stability emerges without invoking unknown physical mechanisms. Long-standing anomalies resolve into expected outcomes. The system no longer appears inexplicably restrained or oddly buffered. It behaves as one would expect from an environment governed by both physical and biological inertia. This realization does not diminish the importance of Megalodon. Instead, it reframes it as part of a broader continuum of scale rather than the apex of possibility. Megalodon represents the largest predator that functioned within a dynamic, transitional ocean. The colossus represents the endpoint of a more stable regime, one that no longer exists. Comparing the two without accounting for environmental context leads to false ceilings and misplaced certainty. The significance of this hypothesis lies not in identifying a specific species, but in recognizing the limits of inference shaped by present conditions. Earth's history is not obligated to conform to modern constraints. The deep past operated under rules that no longer apply, and life responded accordingly. When those rules changed, life changed with them, leaving behind gaps that can only be filled through systems-level reasoning. The story of something larger than Megalodon is therefore not speculative excess. It is a corrective. It reminds us that absence in the fossil record does not equate to absence in reality, especially when dealing with organisms whose primary interaction with the world was through persistence rather than conflict. It urges caution against equating visibility with significance and encourages a broader understanding of how life can function at planetary scale. In this light, the ancient ocean appears not as a place of monsters, but as a system that once allowed biology to merge seamlessly with environment. The Colossus was not an aberration. It was an expression of equilibrium. When equilibrium shifted, that expression disappeared, leaving behind only its imprint on the structure of deep time. That imprint becomes most apparent when considering how modern scientific frameworks instinctively partition influence into discrete categories. Physics governs circulation, chemistry governs nutrients, biology governs organisms. The ancient Colossus collapses these distinctions. It functioned biologically, yet its effects resembled physical moderation and chemical buffering. By existing at sufficient scale and duration, it blurred disciplinary boundaries, which is precisely why it remains difficult to situate within conventional explanations. Systems that defy categorization are often excluded not because they are implausible, but because they are inconvenient. In reconstructing the past, there is a tendency to privilege mechanisms that operate independently of life. Climate shifts, tectonic rearrangements, orbital cycles are treated as primary drivers, while biology is framed as reactive. This hierarchy reflects modern conditions, where no single organism exerts planetary-scale regulation. It does not necessarily reflect the past. In a more stable ocean, biology could afford to become infrastructural. The Colossus represents a moment when life crossed that threshold and briefly assumed a role comparable to physical forces. This perspective alters how extinction itself is interpreted. The disappearance of such an organism does not register as a biological crisis because its role was not tied to biodiversity in a narrow sense. It did not maintain diversity by preventing extinction, but by preventing excess. When it vanished, diversity did not collapse. It expanded, diversified, accelerated. From a biological standpoint, this looks like success. From a systems standpoint, it represents a loss of coherence. Coherence is rarely celebrated because it lacks drama. It does not produce spikes or boundaries. It produces continuity. The geological record, biased toward disruption, struggles to preserve continuity. What it preserves instead is the aftermath, the increase in noise, once the smoothing influence is gone. This creates a misleading narrative in which complexity appears to arise spontaneously rather than as a response to the removal of restraint. The ancient ocean under the influence of the Colossus may therefore be best understood not as a stage for competition, but as a managed system. Not managed by intent, but by consequence. The organism did not regulate because it evolved to regulate. Regulation emerged as a byproduct of its scale and persistence. This distinction matters because it removes any implication of design and places the phenomenon firmly within evolutionary logic. Evolution does not aim, it settles. When conditions remain constant long enough, strategies that minimize fluctuation become viable. Extreme scale is one such strategy. It reduces sensitivity to short-term variability and allows an organism to integrate across space and time. The cost is inflexibility. When variability increases, inflexibility becomes fatal. This trade-off explains both the rise and the disappearance of the Colossus without invoking exceptional circumstances. The modern ocean sits at the opposite end of this trade-off. It rewards rapid response, behavioral plasticity, and redundancy. Influence is distributed among many actors rather than concentrated in one. This distribution creates resilience of a different kind, but it also ensures that no single organism can anchor the system. Stability emerges statistically rather than structurally. The past ocean, by contrast, achieved stability structurally through mass. Recognizing this difference resolves a persistent confusion in comparative ecology. Attempts to project modern dynamics backward inevitably fail because they assume that the same strategies governed both eras. They did not. The rules changed, and with them, the forms that thrived. The Colossus belongs to a rule set that no longer applies. This does not diminish its relevance. On the contrary, it provides a reference point for understanding how life and environment co-evolve. It demonstrates that biological influence is not fixed in magnitude, only constrained by context. Under one set of conditions, life fragments into many fast-moving parts. Under another, it consolidates into fewer, slower ones. Both outcomes are natural. Neither is permanent. The lingering discomfort surrounding the idea of something larger than Megalodon reflects not scientific skepticism, but narrative inertia. Megalodon occupies a cultural role as the ultimate marine predator, a symbolic endpoint. Symbols resist displacement. Yet science is not obligated to preserve symbols. It is obligated to account for evidence, including negative evidence, gaps, and inconsistencies that suggest missing elements. When those elements are considered, the ancient ocean becomes less mysterious. Its apparent overproduction, its unusual stability, its subdued volatility all align with the presence of a massive biological sink. Remove that sink, and the transition to a more chaotic, event-driven marine world follows naturally. No catastrophe required. No anomaly unresolved. The story, then, is not about discovery or proof in the traditional sense. It is about perspective, about learning to read what systems imply rather than what artifacts declare. The Colossus does not need to be named or classified to be understood. Its existence is embedded in the way the past behaves when examined honestly. In the end, the most accurate description of the creature larger than Megalodon may be that it was not an exception to nature, but an expression of it at a scale we no longer witness. The ocean allowed it, sustained it, and then moved beyond it. What remains is not a mystery to be solved, but a lesson in how profoundly context shapes possibility. That lesson extends beyond marine history and into how limits are defined in science more broadly. Upper bounds are often inferred from present observation rather than historical allowance. When something is no longer possible, it is quietly reclassified as having never been possible. This retrospective narrowing creates clean narratives at the expense of accuracy. The ancient ocean resists such narrowing because its constraints were materially different. It tolerated solutions that modern systems cannot sustain, not because those solutions were flawed, but because the boundary conditions that supported them no longer exist. In this context, the Colossus becomes a reference point for understanding how life responds to prolonged equilibrium. Equilibrium is rare in planetary systems, but when it persists long enough, evolution shifts from exploration to optimization. Variation decreases. Scale increases. Energy pathways consolidate. The organism larger than Megalodon represents the endpoint of that optimization process. It was not competing for novelty. It was exploiting predictability. Predictability allows inefficiency to disappear. When food arrives reliably, there is no need to chase it. When conditions remain stable, there is no need to hedge. Size becomes advantageous because it filters noise. Short-term fluctuations that devastate smaller organisms barely register. The Colossus existed above the threshold of disturbance. Storms, migrations, seasonal shifts mattered only insofar as they altered long-term gradients. This mode of existence also explains why intelligence, as commonly understood, would have offered little advantage. Decision-making matters when choices alter outcomes. At extreme scale and long time horizons, outcomes converge regardless of choice. Persistence replaces strategy. The organism did not need to interpret its environment. It needed only to remain aligned with it. That alignment was physical rather than cognitive. Such an organism would not display behaviors recognizable as hunting or avoidance. It would not react to threats because there were none capable of imposing immediate risk. Mortality came not from interaction, but from misalignment with slow environmental change. When stratification weakened and biomass dispersed, the organism did not fail to respond quickly enough. It responded too slowly to respond at all. This slowness is not a flaw. It is a consequence of scale. Every advantage at one end of a spectrum becomes a liability at the other. Speed gains relevance as environments become fragmented. Flexibility matters when predictability vanishes. The Colossus belonged to a world where neither was necessary. When that world dissolved, so did the viability of its largest inhabitant. The absence of drama in this transition is often mistaken for absence of significance. Yet the most consequential shifts in Earth's history are often the least theatrical. Gradual oxygenation, slow cooling, incremental continental drift. These processes reshape life more profoundly than sudden catastrophes, precisely because they alter the background against which all interactions occur. The extinction of the Colossus belongs to this category. It was not a shock. It was a reconfiguration. Modern efforts to detect remnants of such influence often falter because they seek discrete signals. They search for anomalies that stand apart from baseline behavior. But the Colossus defined the baseline. Its removal is encoded not in spikes, but in the emergence of spikes where none previously existed. Variability itself becomes the signal. This inversion challenges intuitive approaches to evidence. It requires comparing not what is present, but how present elements behave relative to expectation. When reconstructed systems appear overly constrained without clear cause, when stability seems unearned, when balances close too neatly, the implication is not that models are correct, but that something is missing. The missing element need not be singular in form, but it must be singular in function. Distributed processes cannot replicate the smoothing effect of a continuous, massive consumer. They approximate it imperfectly through redundancy and feedback. This is what characterizes the post-Colossus ocean. Regulation persists, but it is mediated through many interacting components rather than one dominating presence. This transition mirrors shifts observed in other systems when central stabilizers are removed. Economies without large buffers become more volatile. Ecosystems without keystone species fragment. Physical systems without damping oscillate. The Colossus functioned as damping at biological scale. Its disappearance increased responsiveness at the cost of stability. Understanding this trade-off reframes the narrative of marine evolution. It becomes less about a march toward complexity and more about oscillation between consolidation and dispersion. The ancient ocean consolidated influence into mass. The modern ocean disperses influence across networks. Both strategies are adaptive under different conditions. Neither represents an endpoint. The discomfort provoked by imagining something larger than Megalodon stems from mistaking present dispersion for a universal rule. It is not. It is a phase. Earth has passed through others and will likely pass through more. Under future conditions, scale may again become advantageous. If that happens, life will explore it without hesitation. The story, therefore, is not closed. It is contextual. The creature larger than Megalodon belongs to a chapter written under rules no longer active. Its absence today is not evidence against its past, but confirmation of environmental change. When conditions align, evolution fills available space, whether that space favors minuteness or enormity. What remains is a quieter appreciation of how flexible life truly is. It does not adhere to human expectations of drama or visibility. It adapts to gradients, fills niches defined by physics, and withdraws when those niches collapse. Sometimes, the niche is so vast that the organism filling it becomes indistinguishable from the system itself. In such cases, the end of the organism is not remembered as an extinction, but as a change in how the world behaves. That change in behavior is the true fossil of extreme scale. Long after bodies dissolve and structures vanish, behavior lingers in the architecture of systems. The ancient ocean did not simply lose a species, it lost a mode of operation. Where once energy moved through slow, predictable channels, it began to scatter. Where once excess was absorbed silently, it began to express itself through cycles, surges, and collapses. This shift is subtle enough to escape casual notice, yet fundamental enough to redefine everything that followed. In this sense, the Colossus was less an organism than a phase. Its existence marks a period when the ocean could sustain biological mass as a stabilizing force. When that period ended, the ocean did not regress or fail. It transitioned. The rules governing success changed, and life reconfigured itself accordingly. The disappearance of extreme scale was not an evolutionary dead end, but a strategic withdrawal from a solution that no longer fit. This perspective resolves a lingering contradiction in how ancient seas are described. They are often portrayed as simultaneously abundant and orderly, productive yet strangely restrained. These qualities appear incompatible under modern assumptions, where high productivity usually correlates with volatility. The presence of a massive, slow consumer reconciles this contradiction. Productivity could be high without becoming explosive because it was continuously integrated into a biological sink that operated below the threshold of disruption. Once that sink was gone, abundance and volatility became inseparable. Productivity began to express itself through booms and busts. The ocean became louder in every measurable sense. Chemical gradients sharpened. Biological interactions intensified. Evolutionary pressure accelerated. The fossil record reflects this shift, not as loss, but as proliferation. More forms appear, more interactions leave marks. The story becomes easier to tell precisely because it becomes messier. This ease of narration biases interpretation. A world full of visible interactions feels more real than one governed by quiet regulation. Yet reality does not favor narratability. It favors balance. When balance is achieved through mass and inertia, it leaves little for storytellers to work with. When balance is lost and replaced by constant negotiation, the record fills rapidly. The ancient Colossus belonged to the former world. Its absence defines the latter. It is important to emphasize that this does not imply a superior past. Stability is not inherently better than adaptability. A system optimized for steadiness excels under constancy and fails under change. A system optimized for responsiveness thrives under variability and collapses under sustained pressure. Earth oscillates between these modes. As climate, chemistry, and circulation evolve, life follows, not by choice, but by necessity. Seen this way, the creature larger than Megalodon is not an outlier, but an expected outcome of a particular equilibrium state. Remove the equilibrium, and the outcome disappears. The fact that no modern analog exists is not a problem for the hypothesis. It is its strongest support. Extreme scale requires extreme stability. The modern ocean does not provide it. This understanding also clarifies why attempts to imagine such a creature often default to exaggeration or monstrosity. Without appreciating the environmental context, size appears gratuitous. In reality, it was economical. Large mass reduced sensitivity to noise. Slow movement minimized energetic waste. Continuous feeding eliminated the need for pursuit. What seems excessive when judged by modern dynamics becomes efficient under ancient ones. The Colossus did not evolve to be large for dominance. It evolved to be large because largeness solved the problem its environment presented. When that problem disappeared, so did the solution. The lingering traces of this solution are now misread as anomalies. Overly smooth sedimentation, unexpected energy balances, stability without clear cause. These are not errors in data. They are artifacts of interpretation frameworks that no longer include extreme biological scale as a valid variable. Once that variable is restored, the system behaves as expected. Importantly, this does not require certainty. Science rarely advances through absolute proof in deep time. It advances through explanatory sufficiency. When one hypothesis reduces complexity, resolves inconsistencies, and aligns with known constraints, it earns its place regardless of whether it can be illustrated with a complete skeleton. The creature larger than Megalodon earns that place not because it is dramatic, but because it is useful. It explains more by existing than by not existing. It turns improbability into coherence. It transforms silence into signal. Ultimately, the question is not whether such a creature can ever be definitively demonstrated. The question is whether our understanding of the ancient ocean is complete without it. At present, it is not. Something remains unaccounted for, something large enough to matter, yet quiet enough to be overlooked. The acceptance of that gap does not weaken science. It strengthens it by acknowledging the limits imposed by preservation, perception, and present-day bias. It reminds us that the past operated under different constraints and produced outcomes that no longer fit comfortably within modern intuition. The ancient ocean once allowed life to become so large that it ceased to behave like an organism and began to behave like a condition. When that condition ended, the ocean learned to function without it. We inherited the aftermath, not the cause. What we call mystery is often just a memory we have not yet learned how to read. Reading that memory requires abandoning the expectation of resolution. Some histories do not culminate in a finding, a specimen, or a definitive boundary. They culminate in an altered understanding of scale itself. The ancient colossus belongs to this category. It is not a missing piece waiting to be slotted into a diagram, but a missing dimension that changes how the entire diagram is interpreted. When scale becomes extreme, causality stretches. Effects lag behind actions by years or centuries. Feedback loops lengthen. Systems appear inert even as they are actively shaped. This temporal expansion is as important as physical size. The colossus did not merely occupy space, it occupied time. Its influence accumulated slowly and dissipated slowly. By the time its absence registered, the organism itself was already gone. This delay is critical. It means that no single stratigraphic boundary corresponds neatly to its disappearance. There is no extinction horizon to mark. Instead, there is a gradual drift in system behavior that only becomes apparent in retrospect. Variance increases, stability erodes, adaptation accelerates. These are not signatures of a sudden loss, but of a long withdrawal. Such withdrawals are notoriously difficult to diagnose. They resemble background change. They mimic gradual climate trends. They are easily attributed to multiple small causes rather than one large one. Yet multiplicity often masks singularity. Many small adjustments can be the system's attempt to compensate for the removal of something fundamental. In this case, compensation took the form of redundancy. Where one massive consumer once absorbed excess, many smaller consumers emerged. Where inertia once smoothed fluctuations, feedback networks formed. These networks are flexible but fragile. They respond quickly, but they overshoot. They adapt, but they amplify noise. The modern ocean reflects this condition clearly. Understanding this lineage reframes how modern instability is perceived. It is tempting to see volatility as a defining feature of life, but it may instead be a phase-dependent response. Under long-term stability, volatility is unnecessary. Under instability, it becomes unavoidable. The ancient colossus thrived in the former. Its absence defines the latter. This distinction matters because it alters how limits are inferred. The absence of extreme scale today is often treated as evidence that such scale is biologically unsustainable. In reality, it may simply be environmentally incompatible with current conditions. Sustainability is not absolute. It is conditional. Once this is accepted, the mental barrier to imagining something larger than Megalodon dissolves. Size alone is not the challenge. Context is. Given an ocean that was deeper in its gradients, steadier in its circulation, and richer in predictable biomass, extreme scale becomes not only possible, but efficient. The inefficiency lies in assuming that modern oceans represent a universal template. They do not. They represent a transient state shaped by ongoing cooling, mixing, and disruption. In such a state, speed outperforms mass. Flexibility outperforms endurance. Visibility outperforms influence. These priorities reverse under different constraints. Evolution follows those reversals without sentiment. The ancient colossus left no descendants, not because its strategy was flawed, but because its strategy was too specialized. Specialization always carries risk. When the environment shifts, specialists vanish cleanly, leaving little trace. Generalists persist, but never dominate to the same degree. The modern ocean is a generalist's world. This explains why echoes of the colossus appear fragmented. Traits that once converged in a single organism are now distributed across many. Slow metabolism here, large body size there, deep vertical coupling elsewhere. None combine into the original configuration because the environment no longer rewards that convergence. The blueprint remains viable only in pieces. Those pieces, however, still hint at the whole. They suggest that the ocean once tolerated, and perhaps depended on, a biological presence that modern frameworks struggle to conceptualize. A presence that regulated without reacting, absorbed without competing, and influenced without interacting in ways that leave obvious scars. Such a presence challenges narrative instinct. It offers no drama, no struggle, no moment of triumph or defeat. It simply exists and then ceases to exist, leaving behind a world that behaves differently afterward. This is unsatisfying to storytelling, but faithful to how large systems actually change. The refusal to accept this kind of influence often stems from an implicit bias toward agency. We expect important things to act, to choose, to collide. Yet the most important forces in nature rarely do. They persist, and persistence shapes outcome more reliably than action. The Colossus was persistence embodied. Its story does not end with extinction, because extinction was not its defining feature. Its defining feature was the way it allowed the ancient ocean to remain calm in the presence of abundance. Once that calm was no longer achievable, the organism became unnecessary, and nature does not preserve what it does not need. What remains is a lesson embedded in imbalance. The ancient ocean was not simply a quieter version of the modern one. It was organized around a different solution to the problem of excess. That solution involved life at a scale that no longer fits. To acknowledge that is not to indulge in fantasy. It is to accept that Earth's history includes states that cannot be reverse engineered cleanly from the present. Some answers do not leave artifacts. They leave consequences. The creature larger than Megalodon survives only as such a consequence. Not as a silhouette waiting to be revealed, but as a missing weight whose absence still alters the shape of everything around it. The shape of that absence becomes more defined the longer it is examined, not because new evidence appears, but because existing evidence begins to align differently. Patterns that once seemed coincidental acquire coherence. Relationships that appeared weak strengthen when viewed across broader temporal scales. This is the nature of inference at the limits of observation. It does not accumulate through discovery, but through recontextualization. One of the most persistent misconceptions about biological dominance is that it must be expressed through conflict. This assumption is deeply ingrained, reinforced by visible ecosystems where competition, predation, and extinction are overt. Yet conflict is a feature of crowded systems operating near energetic limits. In environments where energy is abundant and predictable, conflict loses relevance. Regulation replaces competition. The ancient Colossus existed in such an environment. Its dominance was not contested because there was nothing to contest. It did not exclude others through force. It simply occupied a role so large that it reduced the amplitude of everything around it. This role explains why no coevolutionary arms race is visible. Smaller organisms did not evolve defenses against it because defense was unnecessary. Encounter probability was low, and mortality was diffuse rather than targeted. Selection pressures remained governed by other interactions. The colossus operated orthogonally to most evolutionary dynamics. It shaped the background conditions under which evolution occurred without participating directly in evolutionary conflict. This indirect influence is easily overlooked because it violates intuitive models of causation. We expect cause and effect to be proximal. The colossus operated distally. Its feeding altered nutrient availability weeks or months later. Its movement reshaped distribution patterns over seasons. Its presence influenced which ecological strategies were viable without ever interacting with those strategies directly. Such influence is invisible at short timescales and unmistakable at long ones. When examined across millions of years, the ancient ocean exhibits exactly the kind of behavior expected from a system under long-term damping. Extremes are rare, variance is low, transitions are slow. These characteristics are often attributed solely to climate stability, but climate alone does not regulate biological throughput. Without a biological mechanism to absorb excess, even stable climates can produce oscillatory ecosystems. The colossus provided that mechanism. Its removal coincides with a shift toward higher frequency change. Even before major climatic disruptions, biological volatility increases. Species ranges fluctuate more rapidly. Assemblages reorganize more frequently. These changes precede obvious external forcing, suggesting an internal loss of regulation. The system becomes more sensitive, more reactive, more dependent on feedback loops that did not previously dominate. Feedback loops are powerful, but they are also noisy. They amplify perturbations before correcting them. In a system once regulated by inertia, this amplification marks a fundamental change. The ocean transitions from being mass-governed to interaction-governed. This transition is subtle but irreversible. Once the system reorganizes around responsiveness, it cannot easily return to inertia-dominated behavior without restoring the conditions that allow scale to re-emerge. This irreversibility explains why the colossus has no modern analog. It is not merely that we have not found one. It is that the ocean no longer permits the convergence of conditions required for its existence. The necessary combination of depth, stability, nutrient predictability, and long-term equilibrium has been dismantled. Fragmentation has replaced continuity. No single organism can now integrate across the system in the way the colossus once did. Attempts to imagine rediscovery often fail because they project modern instability onto ancient possibility. They assume that any large organism must cope with rapid change, competition, and disturbance. The colossus did not. It existed before those pressures dominated. Its world was quieter in ways that are difficult to reconstruct because quiet does not fossilize. This does not mean the ancient ocean was simple. It was complex, but its complexity was layered rather than tangled. Processes unfolded at different scales without constant interference. The colossus occupied the slowest layer. It did not disrupt faster layers. It stabilized them by absorbing their excess output. When that slow layer vanished, the faster layers began interacting directly, producing the tangled complexity observed thereafter. Understanding this layered structure clarifies why the colossus appears unnecessary when viewed through modern ecological models. Those models assume interaction across scales. The ancient ocean minimized such interaction. Scale separation was greater. Large processes and small processes coexisted without constant coupling. This allowed extreme scale to persist without destabilizing the system. Once coupling increased, extreme scale became a liability. The colossus could not respond quickly enough to rapid shifts propagated across layers. Its inertia, once protective, became fatal. This was not because it failed, but because the architecture of the ocean no longer accommodated its mode of existence. The story, therefore, is not one of hidden survival or undiscovered giants. It is one of historical compatibility. Life explored scale when scale solved a problem. When it no longer did, life withdrew from that solution and reorganized around others. The fossil record preserves the reorganization, not the withdrawal. What remains for modern understanding is not the pursuit of proof in the traditional sense, but the refinement of models to include the possibility of biological influence operating at infrastructural scale. This inclusion does not overcomplicate explanation. It simplifies it. It reduces the need for ad hoc assumptions and reconciles disparate observations under a single principle. That principle is straightforward. Under prolonged stability, life consolidates. Under instability, it disperses. The ancient colossus was consolidation taken to its logical extreme. Its absence marks the end of that phase, not because it was unsustainable, but because the conditions that sustained it dissolved. The ocean moved on. Life adapted. We inherited the consequences. And in those consequences, read carefully and without expectation of spectacle. The outline of something vast and slow still remains, shaping interpretation not through what it left behind, but through what it once made unnecessary. That sense of necessity is the final key to understanding why the ancient colossus feels simultaneously speculative and unavoidable. It occupies the uncomfortable space between imagination and requirement. Remove it from the conceptual model, and explanations proliferate. Add it back in, and many of those explanations collapse into one. This is often how large, slow truths reveal themselves, not through dramatic confirmation, but through explanatory gravity. Explanatory gravity operates quietly. It draws scattered observations toward a center without forcing them. Over time, interpretations begin to orbit the same idea, even if they never touch it directly. In the study of ancient oceans, this gravity appears whenever stability outpaces expectation, whenever energy budgets close too cleanly, whenever variability seems suppressed without sufficient cause. These are not anomalies in isolation. They are hints of a missing stabilizer. The reluctance to name that stabilizer as biological rather than physical reflects a deep-seated hierarchy in scientific thought. Physical forces are assumed to scale smoothly. Biological forces are assumed to fragment. This assumption holds under most modern conditions. It did not necessarily hold in the past. Under prolonged equilibrium, biology can scale upward just as physics does. The colossus represents biology crossing that threshold, becoming less an actor within the system and more a property of the system itself. Once biology reaches this level of integration, it ceases to behave in ways that are easy to isolate. It no longer produces discrete events. It produces background conditions. These conditions persist until they no longer do, at which point the change is felt everywhere but attributed nowhere. The disappearance of the colossus follows this pattern exactly. There is no point at which one can say it ended. There is only a span during which the ocean gradually stopped behaving as if it were there. This gradualism frustrates narrative instinct. Humans seek beginnings and endings. The ancient colossus offers neither. Its emergence was likely incremental, its disappearance diffuse. It did not arrive fully formed. It did not leave suddenly. It grew as stability deepened and receded, as stability eroded. Its life cycle mirrored the life cycle of the conditions that sustained it. Such mirroring reinforces the idea that the organism and the environment were not separate in any meaningful sense. The colossus did not merely inhabit the ancient ocean. It was an expression of it. Its anatomy reflected the density structure of the water column. Its metabolism reflected long-term productivity. Its movement reflected basin scale circulation. To remove it from the ocean is to misunderstand the ocean itself. This is why attempts to classify the colossus as a predator feel inadequate. Predators imply opposition. They imply prey that resists and evolves in response. The colossus did not provoke resistance. It did not define winners and losers. It defined baselines. Its consumption did not alter who survived, only how much accumulated. In doing so, it shaped evolutionary pathways indirectly by constraining the amplitude of ecological experimentation. When that constraint vanished, experimentation accelerated. The fossil record captures this acceleration vividly. Rapid diversification, morphological novelty, increased specialization all follow. This sequence is often celebrated as evolutionary flourishing, and in many ways it is. But it is also a symptom of lost restraint. Diversity expands when boundaries loosen. Stability contracts. Neither outcome is superior. They are responses to different systemic conditions. The ancient colossus belongs to a phase when boundaries were tight, gradients were thick, and change was slow. The modern ocean belongs to a phase when boundaries are thin, gradients are sharp, and change is fast. Life adapts accordingly. The discomfort with accepting something larger than Megalodon stems from conflating present limitation with historical impossibility. Megalodon appears enormous because it exists near the upper bound of what the modern ocean can support. That bound feels natural because it is familiar, yet natural bounds are always conditional. They shift with context. What once lay well within the feasible range may later fall outside it without ever having been flawed. The colossus did not violate limits. It occupied a different limit space, one defined by patience rather than urgency, by continuity rather than reaction, by mass rather than maneuver. When that space collapsed, the organism disappeared cleanly, leaving behind a system that no longer needed and could no longer sustain such an expression. What remains is not a gap in the fossil record, but a gap in perspective. A missing appreciation for how profoundly environment shapes the scale at which life can operate. When that appreciation is restored, the idea of an ancient marine organism exceeding Megalodon in scale becomes neither sensational nor exotic. It becomes a reasonable inference from the behavior of the system as a whole. In the end, the most compelling evidence for the colossus is not found in rocks or reconstructions, but in coherence. The ancient ocean makes more sense when something vast and slow is allowed to have existed within it. Its rhythms align, its balances close, its transitions smooth. The story does not demand belief. It demands allowance. Allowance for the possibility that life once solved the problem of excess, not through speed or complexity, but through scale so extreme that it now survives only as a structural memory embedded in deep time. That allowance reshapes how uncertainty itself is treated. Instead of being seen as a flaw to be eliminated, uncertainty becomes a signal, pointing toward domains where present-day intuition no longer applies. The ancient ocean occupies one of those domains. Its physical parameters, its temporal stability, and its internal organization differed enough from the modern state that conclusions drawn from contemporary analogs lose reliability. In such a context, the absence of a known modern parallel does not weaken an inference. It strengthens it by indicating that the system once operated under a different regime. Within that regime, biological mass could accumulate to a degree that now feels alien, not grotesque or monstrous, but functionally immense. The colossus did not break ecological rules. It exploited a rule set that no longer exists. It converted surplus into continuity. It turned abundance into inertia. In doing so, it allowed the ocean to remain productive without becoming volatile. This conversion is the defining characteristic of its influence, and it is precisely the kind of influence that disappears most completely once removed. Modern reconstructions often underestimate the importance of conversion mechanisms. They focus on sources and sinks, on inputs and losses, but they rarely account for processes that slow circulation itself. The colossus acted as a break embedded within the system, not a barrier, not an obstruction, but a mass that absorbed momentum. Its feeding did not simply reduce biomass. It reduced the speed at which energy moved through the ecosystem. This slowing effect is subtle, but it changes everything downstream. Once energy begins to move faster, systems become more reactive. Feedback loops tighten. Small changes propagate rapidly. Resilience shifts from endurance to adaptability. This is the state inherited by modern oceans. It is not inferior, but it is different. It carries higher variance, greater sensitivity, and lower tolerance for prolonged imbalance. The ancient ocean, under the influence of extreme scale, carried imbalance by distributing it across time rather than space. Time, in this sense, was the true resource exploited by the Colossus. Its lifespan, its growth rate, its feeding strategy all stretched ecological processes across long intervals. Where smaller organisms experience feast and famine, the Colossus experienced continuity. That continuity smoothed the system not because it was designed to do so, but because scale enforces averaging. At sufficient mass, short-term variation becomes irrelevant. This is why the organism cannot be reconstructed meaningfully through isolated traits. Teeth, bones, size estimates all fail to capture its significance. The Colossus was defined less by what it was than by what it prevented. It prevented accumulation beyond control. It prevented rapid oscillation. It prevented the system from fragmenting into countless competing strategies. These prevented outcomes do not fossilize. They appear only as improbabilities when the system is viewed without its stabilizer. As a result, the narrative of ancient marine life becomes skewed toward what proliferated after restraint disappeared. We see diversity explode and assume that explosion is the baseline. We see complexity increase and assume complexity is progress. But these interpretations reflect the properties of an unrestrained system, not a universal condition. The Colossus reminds us that simplicity and restraint can also be adaptive outcomes under different constraints. This reframing does not romanticize the past. It does not suggest that the ancient ocean was better, only that it was governed by different trade-offs. Stability came at the cost of flexibility. When the environment began to change more rapidly, that cost became untenable. The Colossus could not fragment itself into faster, smaller components. It could not hedge against unpredictability. It could only persist or disappear. When persistence ceased to be viable, disappearance followed naturally. That disappearance was clean because nothing depended on the organism in a direct, exclusive way. No species relied on it as prey or shelter. No food web collapsed when it vanished. Instead, the system adjusted by redistributing functions that had once been centralized. Regulation became decentralized. Influence became shared. The ocean learned to operate without its largest component, but in doing so, it became a different system. This difference is now misread as normality. We study the modern ocean and project its properties backward, assuming continuity where none exists. The Colossus challenges that assumption. It stands as evidence that continuity itself is conditional. That the past is not merely a quieter version of the present, but a fundamentally distinct configuration shaped by long-term stability that no longer applies. The difficulty of accepting this lies not in the evidence, but in the implications. Accepting extreme biological scale as a historical reality forces a reevaluation of how limits are defined. It suggests that many constraints we consider fundamental are, in fact, temporary. They emerge from current conditions and dissolve when those conditions change. Life responds accordingly, sometimes in ways that feel excessive only because we no longer inhabit the world that made them efficient. In the end, the story of something larger than Megalodon is not about surpassing a known giant. It is about recognizing that giants themselves are context-dependent expressions of deeper principles. The ancient Colossus expressed a principle of integration through mass. When integration became impossible, mass withdrew, leaving behind a system that learned to integrate through interaction instead. Both solutions are valid, neither is permanent. The ocean has used each in turn and will likely do so again under future conditions we cannot yet imagine. What matters is not whether the Colossus can be named or reconstructed, but whether its absence is acknowledged as meaningful. When it is, the ancient ocean stops appearing incomplete. Its quiet stability, its suppressed extremes, its long plateaus of consistency, all acquire a coherent explanation. The missing weight returns, not as an object, but as understanding. And with that understanding comes a final realization. The largest forces in Earth's history are often the ones that leave the least behind, because their greatest achievement is making everything else appear ordinary while they exist. That ordinariness is deceptive. It masks how radically different the underlying conditions once were. When everything appears stable, when variation is muted and extremes are rare, it is easy to assume that nothing exceptional is present. Yet stability itself can be the signature of something exceptional, operating continuously beneath perception. The ancient ocean did not advertise its most influential component because influence at that scale does not announce itself, it normalizes. Normalization is the most effective form of power in natural systems. It shapes expectations. It defines what is considered baseline. When the baseline shifts, the absence of what once enforced it is rarely recognized as a loss. It is interpreted instead as a change in background conditions, as if the system has always behaved this way. Over time, memory adjusts. The extraordinary becomes unthinkable because it no longer fits the recalibrated frame. This is why the Colossus feels so difficult to hold in mind. It does not violate logic, it violates familiarity. It belongs to a regime where life could afford to be slow, heavy, and vast because the environment rewarded those traits. That regime no longer exists, and without it, the organism appears out of place. But being out of place now does not mean it was out of place then. The temptation to reject such scale often rests on energy arguments framed by modern oceans. Calculations of metabolic demand, prey availability, and growth rates are extrapolated from present conditions and treated as universal constraints. These calculations are internally consistent, but contextually narrow. They assume rapid turnover, patchy productivity, and constant disturbance. Under ancient conditions, where productivity was sustained and spatially coherent, those constraints loosened dramatically. Energy was not scarce in the way it is now. It was concentrated and predictable. Predictability changes everything. It allows organisms to trade flexibility for efficiency. It allows mass to replace speed. It allows continuity to replace reaction. The Colossus was an expression of this trade. Its metabolism did not need to spike. Its feeding did not need to adapt rapidly. Its growth did not need to hedge against failure. It existed in a world where long-term averages mattered more than short-term events. When that world fragmented, averages lost relevance. Events became decisive. Systems began responding to peaks rather than trends. This shift favors a different kind of life. Smaller, faster, more specialized organisms proliferate because they can exploit transient opportunities. Large, slow organisms lose their advantage because continuity no longer exists to exploit. The disappearance of extreme scale is therefore not a mystery of extinction, but a predictable outcome of changing statistical structure. This statistical perspective clarifies why no single line of evidence proves the Colossus outright. Each signal is weak in isolation because the influence itself was diffuse. Strong signals are produced by concentrated interactions. Predation events, mass deaths, sudden disruptions. The Colossus produced none of these. Its influence was spread across space and time. It altered distributions rather than events. It shaped probabilities rather than outcomes. Probability shaping is nearly invisible to fossilization. Fossils record what happened, not what was prevented. They capture collisions, not dampening. They preserve spikes, not suppression. The ancient ocean under extreme biological regulation would therefore leave a record that looks deceptively unremarkable. Only when compared to what follows does the difference emerge. What follows is acceleration, faster evolutionary turnover, sharper ecological gradients, greater sensitivity to external forcing. These changes are often attributed to external drivers alone, but external drivers act differently depending on internal structure. A system with high inertia absorbs shocks. A system with low inertia amplifies them. The removal of the colossus reduced inertia. From that point onward, the ocean responded more visibly to forces that had always been present. This visibility creates the illusion of causation. Climate shifts appear more impactful because their effects are no longer buffered. Tectonic changes appear more disruptive because their consequences propagate faster. In reality, the drivers did not necessarily become stronger. The system simply became less able to absorb them quietly. The ancient colossus functioned as absorption, not in a narrow trophic sense, but in a systemic one. It absorbed variance. It absorbed surplus. It absorbed time. In doing so, it allowed the ocean to remain productive without becoming volatile. Its removal redistributed absorption across many smaller processes, each less capable of smoothing extremes alone. This redistribution is adaptive, but it is not equivalent. It produces a world that feels more dynamic, more responsive, and more fragile. It also produces a world that leaves more traces. From a scientific standpoint, this is convenient. The more the system reacts, the more it records itself. The ancient ocean, regulated by mass and continuity, recorded less precisely because it had less reason to react. Thus, the silence surrounding the colossus is not a failure of evidence, but a consequence of function. It did its job too well to be noticed. Understanding this shifts the burden of proof. Instead of asking why there is so little evidence for something so large, the more appropriate question becomes why the ancient ocean appears so restrained without it. Once framed this way, the inference gains strength. The colossus is not introduced to explain an anomaly. It is introduced to explain normality. Normality, in deep time, is rarely natural. It is usually enforced. The enforced normality of the ancient ocean suggests a regulator whose scale exceeded that of conventional predators. Whether it is ever described in anatomical detail is secondary. Its role is already legible in the way the system behaved when it was present and how that behavior changed when it was gone. In the end, the story does not require a final revelation. It does not hinge on discovery or validation. It stands as an example of how understanding advances when scale is treated not as an embellishment, but as a variable capable of redefining what life can be. The ancient ocean once allowed life to become so large that it faded into the background of its own influence. When that influence withdrew, the background came into focus, and we mistook the new sharpness for truth. What is being recovered now is not a creature, but a way of seeing. A recognition that some of the most powerful forms of life leave behind no monuments, only systems that behave differently once they are gone. That difference is the only trace they ever needed to leave. That way of seeing carries implications far beyond a single hypothetical organism. It forces a reconsideration of how biological influence is measured at all. Modern metrics, privilege immediacy, rates of predation, population turnover, visible impact. These metrics are appropriate for systems dominated by short cycles. They fail when applied to systems governed by long integration times. The ancient colossus operated on integration times so extended that its influence cannot be captured by snapshots. It must be inferred through cumulative effect. Cumulative effect is easily mistaken for background. When a force acts continuously over long periods, its contribution becomes indistinguishable from the structure of the system itself. Remove it, and the structure deforms. Yet that deformation is gradual enough to be misattributed to everything except the missing force. This is precisely what happened when the Colossus vanished. The ocean did not collapse. It subtly rebalanced. Over time, those rebalancings compounded into a state so different from the original that the original became unimaginable. Imagination is constrained by reference. Without a living analog, scale becomes abstract. Megalodon persists in cultural memory, not only because of its size, but because its form aligns with familiar predatory logic. Teeth, speed, aggression, dominance. It fits a story humans understand. The Colossus does not. It offers no clear narrative hook. It is neither hunter nor monster, neither threat nor spectacle. It is simply there, and then not. This lack of narrative shape makes it uncomfortable. Humans are inclined to reject what cannot be storied. Yet nature is under no obligation to produce entities that fit narrative expectations. Most of its work occurs outside the bounds of drama. Regulation, buffering, absorption, inertia. These are unglamorous processes, but they are foundational. The Colossus belonged to this category. Its significance lies not in what it did, but in how much it allowed everything else to remain unchanged. The ancient ocean's long periods of apparent equilibrium are therefore not passive states. They are actively maintained conditions. Energy does not distribute itself evenly without mediation. Biomass does not remain stable without sinks. Variability does not suppress itself spontaneously. Something must absorb excess, and in the absence of sufficient physical mechanisms, biology fills that role. The Colossus was biology operating at that threshold, large enough to matter where physics alone could not. Once that biological buffer was gone, physical forces asserted themselves more visibly. Circulation intensified, mixing increased. Gradients sharpened. Life adapted by becoming faster and more fragmented. This adaptation is often framed as an evolutionary triumph, but it is equally an admission that a different mode of stability was lost. Triumph and loss are not mutually exclusive. They are different descriptions of the same transition viewed from different scales. At the scale of species, diversification looks like success. At the scale of systems, increased volatility looks like vulnerability. The ancient Colossus traded diversity for steadiness. The modern ocean trades steadiness for diversity. Neither trade is inherently superior. Each reflects the constraints imposed by the environment at the time. This reframing dissolves the expectation that the past must always be more primitive or less capable than the present. In some respects, it was more capable. It sustained forms of integration that modern conditions no longer allow. It supported biological masses that could regulate entire basins quietly and persistently. The loss of that capacity is not a sign of progress or decline. It is a sign of change. Change, however, is often misread as inevitability. The current state of the ocean feels permanent because it is the only one experienced. Yet deep time is a record of impermanence. States that persist for tens of millions of years still end. Strategies that dominate vanish. Constraints shift. Life reorganizes. The Colossus is one such vanished strategy, preserved only in the negative space it left behind. Negative space is difficult to study because it requires resisting the impulse to fill gaps with assumptions. It demands patience and restraint. Instead of asking what is missing, it asks what is different because something is missing. This shift in questioning opens a new interpretive pathway. The ancient ocean's unusual calm, its muted extremes, its long plateaus of consistency, all become signals rather than curiosities. Through this lens, the creature larger than Megalodon is no longer an outlier to be justified. It is a solution to a problem the ancient ocean demonstrably had: how to remain productive without becoming unstable. The modern ocean solves this problem differently. That difference is the true boundary between eras. What makes this story compelling is not its scale, but its restraint. It does not demand belief in hidden monsters or lost worlds. It asks only that biological influence be allowed to scale with opportunity. When opportunity contracts, influence contracts. When opportunity expands, influence expands. Evolution follows opportunity relentlessly. The ancient Colossus was opportunity embodied. A long window of stability, depth, and abundance converged, and life responded by consolidating. When that window closed, consolidation ceased. The result is not mystery, but continuity of process. In the end, the most accurate conclusion is also the least dramatic. The ocean once supported a form of life whose scale matched the calm of its world. That calm is gone. The life that depended on it is gone with it. What remains is a faster, noisier ocean whose history feels incomplete only because one of its most important chapters was written in a language that leaves no direct trace. Understanding that language does not require discovery. It requires listening to what the system does when the words are no longer spoken. Listening in this way means accepting that some explanations will never condense into a single object of study. They remain distributed, readable only through convergence. This is uncomfortable for disciplines built on classification and enumeration, but it is unavoidable when dealing with phenomena whose defining characteristic was continuity rather than discreteness. The ancient Colossus belongs to this class. It cannot be isolated without losing what made it relevant. To extract it from context is to misrepresent it. The ocean that sustained such a presence was not merely a container, it was a partner in function. Water density, pressure gradients, and thermal layering all contributed to a regime in which mass could persist without constant correction. The organism's body did not fight the medium. It yielded to it. Movement was not propulsion so much as accommodation. In such a regime, efficiency was achieved not by minimizing resistance, but by aligning with it. The Colossus did not overcome the ocean. It matched it. This matching explains why its existence leaves no obvious disruption in contemporaneous records. There was no shockwave associated with its movement, no abrupt displacement of other large fauna, no signs of ecological panic. Everything else simply operated around it, as systems tend to do around stable features. Mountains do not frighten weather systems, they redirect them. The Colossus functioned similarly, redirecting flows of biomass and energy without eliciting reaction. Once that redirection ceased, flows changed course, not dramatically, but enough to matter. New pathways formed, old ones weakened. Over long spans, these small adjustments accumulated into a different ocean. The fact that this transformation can be described without referencing any single extinction event is precisely what makes it so difficult to attribute. There is no smoking gun, only a slow shift in baseline behavior. This slow shift also explains why debates about maximum size in marine life often stall. Arguments are framed around mechanics and metabolism as if those factors exist independently of system-level context. They do not. Mechanics operate within regimes. Metabolism scales with predictability. Remove predictability, and previously viable solutions collapse. Add predictability, and constraints loosen. The ancient ocean loosened them enough for scale to become dominant. It is tempting to ask why such an organism evolved only once, or why it did not leave multiple lineages. The answer lies in convergence. Extreme scale is not a branching strategy. It is a terminal one. Once achieved, there is nowhere further to diversify without fragmenting. Fragmentation defeats the purpose of scale. The Colossus did not give rise to many forms because multiplicity was unnecessary. Its success lay in singularity. Singularity, however, is fragile. It depends on conditions remaining favorable. When those conditions erode, singular strategies fail quickly and completely. There is no redundancy, no fallback. This is why the disappearance of the Colossus appears so clean. It did not fragment into smaller descendants. It simply ceased to be viable and vanished. The ocean did not mourn this loss. Systems do not mourn. They adapt. Adaptation, in this case, meant redistributing functions that had once been centralized. That redistribution increased complexity and responsiveness, but also introduced new vulnerabilities. The modern ocean carries those vulnerabilities openly. It fluctuates more, reacts faster, and leaves clearer records of stress. In doing so, it offers more data but less stability. From a human perspective, this trade feels natural because it aligns with experience. We live in a world of rapid feedback and visible consequence. The ancient ocean, governed by slow integration, feels abstract by comparison. Yet abstraction is not absence. It is scale beyond immediacy. The persistence of questions surrounding ancient marine stability suggests that something fundamental is still being missed when interpretations rely solely on modern analogs. Each time models require fine-tuning to suppress variance, each time unexplained buffering is invoked, the shadow of the Colossus reappears, not as a hypothesis demanding acceptance, but as a possibility demanding consideration. Consideration is all that is required. The existence of something larger than Megalodon does not overturn known facts. It contextualizes them. It places known giants within a broader spectrum of solutions, rather than at its limit. It reframes extinction patterns, stability metrics, and evolutionary pacing as responses to shifting regimes rather than isolated phenomena. Ultimately, the ancient Colossus serves as a reminder that life does not merely occupy environments. It participates in shaping their operating modes. Under certain conditions, that participation can scale until it becomes indistinguishable from the environment itself. When that happens, the removal of life reshapes reality more profoundly than its presence ever did. The deep ocean still carries traces of this principle, not as memory, but as structure. It behaves as a system that once relied on mass and now relies on motion. That transition defines much of what is observed today. It explains why modern oceans feel both energetic and unstable, productive and fragile. There is no need to imagine hidden survivors or lost monsters to appreciate this history. The truth is quieter and more instructive. The largest influence may already be gone, and yet its absence continues to shape everything that followed. Understanding that absence does not complete the story. It opens it, revealing that what we consider limits are often just the boundaries of the present moment, mistaken for universal law. In deep time, such mistakes are temporary. Context shifts, constraints dissolve, and life responds in ways that later generations struggle to imagine. The ancient ocean allowed life to become vast enough to vanish without trace. The modern ocean does not. That difference is not a mystery. It is the story itself. The story reaches its quiet conclusion not by closing a circle, but by widening it. Once the possibility of extreme biological scale is admitted as conditional rather than forbidden, the ancient ocean no longer appears incomplete or strangely restrained. It appears optimized for a different objective than the one governing modern seas. That objective was not speed, not diversity, not constant adaptation, but endurance. Endurance expressed not through resistance, but through mass integrated over time. In such a system, change was not resisted actively. It was absorbed passively. Variations in productivity, temperature, or circulation did not propagate rapidly because they encountered inertia at biological scale. The Colossus functioned as that inertia. Its sheer persistence stretched cause and effect across intervals, long enough to prevent sharp responses. The ocean behaved as if buffered because it was buffered, not by physics alone, but by life occupying the slowest possible tempo available to it. This insight reframes the ancient ocean as a place where biology and environment converged toward the same solution. Physics provided the stability, biology exploited it, and together they produced a system that minimized surprise. Surprise is expensive. It demands rapid response, redundancy, and loss. A system that avoids surprise conserves energy at every level. The Colossus was an expression of that conservation, a living reservoir into which excess quietly flowed. When the physical conditions supporting this convergence began to erode, biology could not preserve the arrangement on its own. Life does not impose stability against persistent change. It aligns with what exists. As stratification weakened and circulation accelerated, the advantage of extreme scale evaporated. The Colossus did not fail in competition. It simply ceased to be aligned with the system that once sustained it. This misalignment explains the absence of drama in its disappearance. There was no battle, no threshold, no final moment. There was only a gradual loss of efficiency, followed by demographic thinning, followed by silence. The system adjusted around that silence until it no longer remembered what had filled it. New baselines formed, new strategies dominated. The ocean became something else. From the vantage point of the present, that transition is easy to misread as inevitability. The modern ocean feels like the default state because it is familiar. But familiarity is not universality. The deep past was governed by parameters that no longer apply, and under those parameters, solutions emerged that now feel counterintuitive. Extreme scale is one of them. The reluctance to accept such solutions often stems from the expectation that evidence must be tangible. Yet the most powerful forces rarely leave tangible traces proportional to their influence. They leave structural consequences. They alter how systems behave after they are gone. In this case, the consequence is a more volatile, more reactive, more fragmented ocean, whose behavior contrasts sharply with its earlier steadiness. Seen through this lens, the ancient Colossus becomes less a subject of speculation and more a tool of understanding. It clarifies why certain patterns appear too smooth, why certain balances close too neatly, why the transition to modern dynamics feels abrupt despite lacking a singular cause. It provides continuity where otherwise only coincidence exists. There is no requirement to imagine its shape precisely, to assign it a lineage, or to anchor it to a specific fossil. Its relevance does not depend on anatomical certainty. It depends on functional necessity. If a system behaves as though regulated and no physical regulator suffices, then biological regulation at sufficient scale becomes not exotic, but reasonable. Reasonableness, however, does not guarantee comfort. Accepting that life once operated at scales now inaccessible forces humility. It reminds us that present limits are contingent, that absence is often historical rather than absolute, and that the largest chapters of Earth's story are not always written in forms we can recover directly. The ocean does not remember in narratives. It remembers in gradients, in circulation, in the tempo of change. The ancient Colossus is embedded in that memory not as an object, but as a former condition. Its influence persists not because it survives, but because the system that replaced it still carries the imprint of having once relied on something vast, slow, and quiet. In the end, the idea of something larger than Megalodon is not an escalation of wonder. It is a reduction of surprise. It makes the ancient ocean more intelligible, not more mysterious. It explains why stability once prevailed without constant conflict, why abundance did not immediately become chaos, and why the modern ocean feels like a system always in motion, always responding, always on the edge of imbalance. The past did not require monsters to be extraordinary. It required conditions. Given those conditions, life responded with a solution that matched them exactly, and then withdrew when they changed. What remains is not a legend, not a fear, not a discovery waiting to happen, but a recognition that scale itself is one of evolution's tools, used when appropriate and abandoned when no longer needed. That recognition is enough. It completes the outline without filling it in, respects the silence without mistaking it for emptiness, and allows the ancient ocean to be understood on its own terms. As a world that once made room for life so large that its greatest achievement was becoming indistinguishable from the sea that carried it. That indistinguishability is the final boundary where organism and environment dissolve into one another. Beyond it, the language of biology becomes inadequate, and the language of systems takes over. The ancient colossus existed beyond that boundary. It was alive, yet its influence resembled climate more than behavior. It fed, yet its feeding registered as regulation. It moved, yet its movement altered distributions rather than provoking reaction. To insist on seeing it as a predator in the conventional sense is to compress something fundamentally expansive into a frame too small to hold it. What matters most is not how the organism looked, but how it functioned across scales. Its size mattered less as a number than as a property. Scale transformed interaction into background condition. At that magnitude, cause and effect blurred. Actions lost sharp edges. Everything became averaged. This averaging is the defining characteristic of systems governed by inertia. The ancient ocean possessed such inertia not only physically, but biologically. The colossus was the biological expression of that inertia. Once inertia declined, everything sped up. Processes that once unfolded over centuries compressed into decades. Feedback loops tightened. Systems that had relied on mass to buffer change were forced to rely on speed instead. This transition did not create a better ocean or a worse one. It created a different one, a more reactive one, a more legible one, a more fragile one. Legibility is deceptive. Because modern oceans leave clearer records of interaction, it feels as though they are better understood. In reality, they are simply louder. The ancient ocean, quieter and slower, resists interpretation because its dominant forces did not manifest as discrete events. They manifested as restraint. Restraint does not leave signatures easily. It leaves absence of extremes, which is only recognizable when compared to what comes after. This comparison reveals the true magnitude of what was lost. Not a species, but a mode of regulation. Not a giant, but a stabilizing presence so pervasive that it vanished without notice. Only when volatility increased did the absence become meaningful. Only when the ocean began to oscillate did it become clear that something had once prevented it from doing so. Such prevention is rarely credited. Systems that remain stable are assumed to be naturally stable. Systems that fluctuate are studied intensely. This bias skews interpretation of the past. The ancient ocean's calm is treated as a default state rather than as an achievement. The colossus reframes that calm as the outcome of biological participation at unprecedented scale. Accepting this reframing does not require abandoning skepticism. It requires redirecting it. Skepticism should ask not only whether evidence supports existence, but whether alternative explanations adequately account for observed stability. When they do not, the cost of exclusion rises. The colossus persists not because it is proven, but because it is economical. It explains much without complicating anything unnecessarily. Economy of explanation is often mistaken for conservatism. In this case, it demands expansion rather than contraction of imagination. Not expansion into fantasy, but into scale. Scale is not speculation. It is measurable. It obeys constraints. It responds predictably to stability. Under the conditions inferred for ancient oceans, scale becomes a logical outcome rather than an aberration. The reluctance to move beyond Megalodon as an upper bound reflects attachment to a known extreme. Known extremes feel safe. Unknown ones threaten closure. Yet closure is not the goal of understanding deep time. Coherence is. The Colossus contributes to coherence by aligning disparate observations into a single systemic narrative. That narrative does not culminate in revelation. It culminates in perspective. It teaches that the absence of drama is not the absence of influence, that the most powerful forms of life may be those that operate too slowly to be noticed, and that extinction can occur not through violence, but through irrelevance, when the world no longer needs what once held it together. The ancient ocean needed mass. It needed inertia. It needed something that could exist without reacting, absorbing excess without altering form. For a time, life provided that. When conditions changed, life withdrew from that role and reorganized around others. The ocean adapted, as it always does. What remains for the present is not a search for confirmation, but a recalibration of limits, to understand that what feels impossible now may have been inevitable then. That evolution does not seek spectacle, only sufficiency, and that sometimes sufficiency takes the form of something so large, so slow, and so quiet that its greatest trace is the way the world behaves differently after it is gone. In that difference lies the final evidence, not a bone, not a tooth, not a silhouette rising from the depths, but a shift in how stability itself is understood. The creature larger than Megalodon existed not to be seen, remembered, or discovered, but to make an entire ocean behave as though nothing extraordinary was happening at all. That ordinariness, sustained over immense spans of time, is the most difficult condition for modern thinking to reconstruct. Human cognition is tuned to notice deviation, not consistency. We detect spikes, not plateaus. We record disruptions, not continuities. The ancient ocean, regulated by a presence whose influence was everywhere and nowhere at once, existed largely as a plateau. It changed, but it changed slowly enough that its changes merged into expectation. This is why the removal of that presence is felt not as loss, but as acceleration. Only when the pace increases does the former stillness become visible in retrospect. Acceleration reshapes memory. Once systems begin to fluctuate more rapidly, earlier states appear static, even artificial. They are assumed to have been held in place by physical constraints alone. Yet physical constraints do not produce biological smoothness. They shape boundaries, not flows. The smoothness of the ancient ocean's biological output suggests mediation, and mediation at that scale cannot be achieved through countless small interactions without producing noise. Noise suppression requires averaging. Averaging requires mass. The Colossus was mass applied to biology. Its scale ensured that local variation disappeared into global consistency. Where productivity spiked, it absorbed. Where productivity waned, it persisted. This persistence mattered more than consumption. It prevented the system from overreacting to its own abundance. In doing so, it allowed evolutionary processes to proceed under unusually calm conditions. Selection pressures remained gentle. Extremes were rare. Lineages had time to refine rather than scramble. This calm is evident in the tempo of change recorded in deep time. Morphological shifts proceed gradually. Ecosystems maintain structure over long intervals. The absence of rapid turnover is striking when contrasted with later periods. Such restraint is often attributed to environmental uniformity, but uniformity alone cannot explain biological moderation. Without regulation, even uniform environments generate oscillations. Something must actively smooth the output. The Colossus fulfilled that role not by intent, but by inevitability. Its feeding did not target. Its movement did not seek. Its existence intersected with excess wherever excess arose. This intersection was statistical, not behavioral. It did not need to know where abundance was. Abundance emerged along the same gradients that sustained it. They co-occurred because both were expressions of the same underlying stability. When that stability eroded, the coincidence dissolved. Abundance became transient. The Colossus could no longer remain aligned with it. Its strategy failed not because it was inefficient, but because it was no longer matched to the environment's geometry. Geometry, in this context, refers not to space alone, but to the shape of time, predictability, and flow. The ancient ocean had a geometry that favored persistence. The modern ocean favors responsiveness. Responsiveness leaves traces. Persistence erases them. This inversion explains why the fossil record becomes richer as the Colossus disappears. More interaction produces more marks. More marks create the illusion of increased importance, yet importance does not correlate with visibility. The most influential forces often operate precisely by minimizing visible effect. Modern science, increasingly aware of this bias, has begun to recognize similar patterns in contemporary systems. Large-scale ecological regulators are often underestimated until they are removed. Only then does their absence produce cascading effects that force recognition. The ancient Colossus represents this phenomenon taken to its extreme. It was so effective at regulation that its existence became invisible. This invisibility should not be confused with subtlety. The influence was enormous. It shaped nutrient cycling, population dynamics, and evolutionary tempo across entire basins. But it did so without concentrating impact at any one point. Concentration attracts attention. Distribution disappears into background. The Colossus chose, by virtue of scale, the latter. As understanding deepens, the resistance to this idea weakens. The notion of a biological presence operating at infrastructural scale no longer seems radical when viewed alongside modern realizations about ecosystem engineers, keystone species, and biogeochemical coupling. The difference is only one of magnitude. The ancient ocean permitted that magnitude to grow unchecked because it remained stable long enough for convergence to occur. Convergence is slow. It requires time without interruption. The ancient ocean provided that time. When interruptions increased, convergence reversed. Divergence took over. Diversity increased. Volatility rose. The system became more interesting, more dramatic, more visible. It also became less anchored. Anchoring is what the Colossus provided. Not direction, not control, but weight. Weight slows motion. Weight smooths gradients. Weight makes systems resistant to sudden change. Once weight is removed, motion accelerates, whether intended or not. This is the final implication of the story. The creature larger than Megalodon was not remarkable because it was bigger. It was remarkable because it carried weight in a biological sense. It anchored an oceanic regime. When that anchor lifted, the ocean did not drift aimlessly. It reorganized around new principles. Those principles define the world that followed and the world that exists now. The ancient ocean, therefore, should not be imagined as a place of lurking giants, but as a system stabilized by one. The distinction matters. One implies fear and spectacle. The other implies function. Function leaves fewer stories, but deeper consequences. What remains is an understanding that the limits we perceive today are not inherent ceilings, but reflections of present alignment. When alignment changes, so do limits. The past reminds us of this, not through artifacts, but through contrast. The contrast between a world that moved slowly because it was held together by mass, and a world that moves quickly because that mass is gone. The creature larger than Megalodon does not haunt the ocean. It does not hide in trenches or await rediscovery. It exists only as a former solution to a former problem. Its relevance lies not in what it was, but in what it allowed everything else to be while it existed. And that, ultimately, is why its story continues to unfold not as revelation, but as recognition. Recognition, once it settles, changes the direction of inquiry. Instead of asking where the creature went, attention shifts toward what kind of world could produce it in the first place. This is a far more productive question. because it does not depend on recovery or proof, only on consistency. The ancient ocean must be understood as an environment that rewarded patience more than reaction, continuity more than agility, and accumulation more than innovation. Under those priorities, extreme scale was not an anomaly, but a natural endpoint. Such an endpoint does not arise suddenly. It emerges slowly as selective pressures flatten. When threats diminish, when resources arrive reliably, when variability remains low across generations, selection begins to favor traits that minimize expenditure rather than maximize opportunity. Size grows because it filters disturbance. Lifespan extends because mortality decreases. Growth slows because urgency disappears. Over millions of years, these tendencies converge. What results is not a monster, but a system participant whose scale reflects the calm of its surroundings. The modern impulse to associate size with aggression obscures this logic. In reality, the largest organisms tend to be the least reactive. Reactivity is costly. It requires rapid energy mobilization and constant sensory processing. In stable environments, those costs outweigh benefits. The ancient colossus did not need to respond quickly because nothing forced it to. Its success depended on remaining aligned with large-scale gradients, not on winning moment-to-moment encounters. This alignment also explains why its presence did not suppress biodiversity. It did not monopolize resources in a way that excluded others. Instead, it skimmed excess from a system capable of producing more than smaller consumers could process smoothly. By doing so, it reduced the amplitude of fluctuations that would otherwise destabilize communities. Diversity thrived, not in spite of the colossus, but partly because of it. Stability creates space for specialization without crisis. When that stability declined, specialization became riskier. Narrow strategies failed quickly. Generalists proliferated. The ocean entered a phase where adaptability mattered more than refinement. This shift is visible in the fossil record as increased turnover and experimentation. It feels like progress because it produces novelty, but novelty is not inherently beneficial. It is simply what emerges when constraints loosen. The ancient colossus represented the opposite condition. Constraints were strong but gentle. They shaped outcomes without forcing change. Life adapted slowly because it could afford to. Evolution under such conditions favors endurance over brilliance. It favors solutions that last rather than solutions that excel briefly. Extreme scale is one such solution. It is dull in the short term and unbeatable in the long term, until the long term itself changes. This is why the disappearance of the colossus feels anticlimactic. There was no failure point, no decisive moment when size became disadvantageous. Instead, the environment gradually shifted away from the parameters that made size economical. Costs rose incrementally. Benefits diminished incrementally. At some point, reproduction could no longer offset loss. The population thinned below recovery. The organism vanished, not because it was outcompeted, but because it no longer fit. Fit is the core concept here. Life does not persist because it is strong, clever, or large. It persists because it fits. The ancient ocean fit extreme scale. The modern ocean does not. This truth dissolves the need for drama, mystery, or speculation about survival. The story is complete without survivors. Its lesson lies in conditionality. Conditionality is often uncomfortable because it undermines absolutes. It suggests that what seems impossible today may have been trivial yesterday, and what seems fundamental now may be temporary. The colossus embodies this discomfort. It stands as evidence that biological ceilings are not fixed. They are negotiated between life and environment, and those negotiations change over time. Understanding this reframes the role of Megalodon itself. Megalodon becomes not the apex of marine predation, but the largest expression of a later, more dynamic, oceanic regime. It was optimized for pursuit impact, and interaction. It thrived in a world where variability demanded responsiveness. The Colossus thrived in a world where variability was muted and responsiveness unnecessary. They represent different answers to different questions posed by different oceans. Seen this way, comparison between them is misleading. Size alone does not determine dominance. Context does. The ancient Colossus was dominant because dominance meant persistence. Megalodon was dominant because dominance meant control. Both were optimal within their respective systems. Neither invalidates the other. The tendency to treat one as the ultimate limit reflects a desire for closure rather than understanding. Nature does not provide closure. It provides sequences. Each sequence ends when its conditions end, not when it reaches an inherent maximum. The Colossus did not represent the maximum possible size of life. It represented the maximum useful size under a particular configuration of the ocean. Once that configuration dissolved, usefulness contracted. Life retracted from scale, not because it could not sustain it, but because it no longer needed it. Evolution is economical. It abandons expensive solutions when cheaper ones suffice. Extreme scale is expensive. It is only worth maintaining when it solves a problem no other strategy can solve as effectively. The ancient ocean had such a problem: how to absorb abundance without chaos. The Colossus solved it. The modern ocean solves the same problem through fragmentation, feedback, and speed. The solution changed. The problem remained. This continuity of problem across different solutions is the final coherence of the story. It shows that the presence or absence of a creature larger than Megalodon is not arbitrary. It is tied directly to how the ocean manages excess. When excess is continuous and predictable, life consolidates. When excess is intermittent and chaotic, life disperses. The past, therefore, is not a place of exaggeration, but of alignment. The Colossus aligned with its world so completely that its influence vanished into normality. When that alignment broke, the world became louder, and the quiet giant slipped into silence without protest. Nothing about this requires myth. It requires only the willingness to accept that some of the most important actors in Earth's history are not remembered because they never needed to announce themselves. Their work was done in averages, not events, in continuity, not conflict, and in scale so large that it dissolved into the sea itself. The conclusion, then, is not a revelation, but a settling. The ancient ocean does not yield its deepest truths through discovery in the usual sense. It yields them through coherence. When its behavior is examined without forcing it into modern constraints, a different logic emerges, one in which life and environment are not adversaries or separate layers, but components of a single operating system. Within that system, extreme biological scale was not excess, it was balance. The creature larger than Megalodon existed because balance required it. Not balance in the poetic sense, but in the mechanical one. Energy entered the system steadily. Biomass accumulated predictably. Physical processes alone could not dissipate that accumulation without inducing instability. Biology stepped into that gap, and over time, it did so at a scale commensurate with the problem. The result was a living process so large and so slow that it ceased to register as an organism and became a condition of the ocean itself. When that condition was no longer necessary, it disappeared without ceremony. No collapse followed because nothing had been built in dependence on it. The system had relied on it implicitly, not explicitly. Once gone, the ocean reorganized around faster, noisier mechanisms. These mechanisms left clearer traces, richer fossils, sharper transitions. They also produced the illusion that history had become more active, more dramatic, more alive. In reality, life had not intensified. It had redistributed. The ancient calm was not emptiness, it was regulation. The modern turbulence is not chaos, it is compensation. Both states are intelligible, once the missing scale is acknowledged. Without that acknowledgement, the past feels oddly restrained and the present oddly unstable. With it, both make sense as phases governed by different constraints. Nothing further needs to be proven for this understanding to hold value. It does not rest on finding a specimen or naming a lineage. It rests on accepting that life is capable of operating at scales that modern conditions no longer permit, and that the absence of such scale today is not evidence of impossibility, but of change. The ocean once allowed something larger than Megalodon to exist because it needed something like it. When the need ended, so did the solution. What followed was not loss, but transition. The world moved from a regime of endurance to one of responsiveness, from mass to motion, from quiet stability to visible complexity. That transition defines the boundary between the ancient sea and the modern one. The story ends there, not because the idea is exhausted, but because it has reached its proper form. It is not a tale of monsters or secrets waiting to be uncovered. It is an account of how scale, when permitted, becomes invisible through effectiveness, and how its disappearance reshapes everything without leaving a monument behind. What remains is understanding, the recognition that some of the greatest forces in Earth's history did not announce themselves, did not leave trophies, and did not demand remembrance. They simply worked until the world no longer required their work. And when they were gone, the ocean learned to live without them.
We upload new videos every single day, so make sure to subscribe and turn on the notification bell so you never miss what's next. If you enjoyed this video, don't forget to leave a like, it really helps the channel grow. Tell us in the comments what you'd like to see next. Your ideas might be in our next upload. Thank you so much for watching and for being part of our community. Stay tuned, stay curious, and we'll see you in the next video.